Good morning, everyone. Welcome to our 2022 Aquifer Storage and Recovery Peer Review Panel Workshop. My name is Liz Caneja, and I'm a project manager in the Ecosystem Restoration and Capital Projects Division at the South Florida Water Management District and serve as the planning project manager on the Lake Okeechobee Watershed Restoration Project, also referred to as LORP. LORP has an Aquifer Storage and Recovery component, or ASR component, and I am continuing as the project manager as we transition from planning into design and implementation of this feature. LORP is a comprehensive Everglades restoration plan, or a SERP project, and it is a cost share project between the federal sponsor, the U.S. Army Corps of Engineers, referred to as the Corps, and the non-federal sponsor, the South Florida Water Management District, referred to as the district. I want to welcome and thank everyone for joining us today to discuss this very important and necessary component needed for Everglades restoration. And we are excited to share with you what we have been working on and the progress made since we last met with the ASR peer review panel back in 2020 and since completion of the 2021 ASR science plan. The purpose of today's meeting is to discuss the ASR science studies conducted, share a summary of the results, and demonstrate the ASR progress. We will be conducting our workshops similar to the previous workshops held in 2020, where we are seeking input from an independent group of scientists to review aspects of the ASR program and provide recommendations on its regional implementation in South Florida. Before we get started, I would like to thank our panel members for participating in the 2022 ASR Science Plan Review and also introduce our peer review panel members. First, we have Dr. Tom Mismer. He is the ASR Peer Review Panel Chair and is an executive in residence professor at the UA Whitaker College of Engineering at Florida Gulf Coast University. He is a professional geologist in Florida with nearly 50 years of experience in the groundwater development, water management, and remediation of groundwater contamination. He served on the ASR Peer Review Panel previously. Dr. Renee Price is a returning peer review panelist and is a professor at Florida International University. Her focus has been on chemical hydrogeology, stable isotope hydrology, saltwater intrusion, and sea level rise. She has conducted hydraulic investigations in South Florida related to Everglades restoration for over 20 years. Mr. Reed Heil is also a returning peer review panelist. He is a lifelong fisherman turned biologist that holds a bachelor's degree in fishery science and a master's degree in marine science. He has been with the Florida Fish and Wildlife Conservation Commission for nearly 20 years as a biological scientist. Dr. John Carragher is a new peer review panelist and has many years of experience in ecological risk assessment. He is currently a research physical scientist at the Environmental Protection Agency's Office of Research and Development in Cincinnati, Ohio. His work at the EPA has been focused on development of environmental management and ecological risk assessment methods for complex problems. Also, I would like to introduce some of our ASR key team members from the district and the Corps that are either involved with the LORP planning effort, the ASR WELL program, or assisted with the preparation of the draft 2022 ASR science plan. From the district, we have Jennifer Gent, which is our lead engineer and project manager for the ASR component. Dr. Anna Washnika, which is our lead scientist for the ASR science plan and project manager for ecological studies and risk assessment. We have Bob Verastro, which is a principal hydrogeologist and lead author of the ASR science plan, which formerly led the ASR pilot studies and also the ASR regional study. And Liz Geddes, she is a principal hydrogeologist that is managing several contracts related to geological studies pertaining to the ASR science plan. From the U.S. Army Corps of Engineers, we have Tim Geisen, which is the project manager of LORP, and he's been on the project team since 2016. We have Jim Hurricane. He is currently transitioning as the new project manager of LORP and the ASR component and will be taking over Tim's role. We have Joel Galliard. He's the lead engineer for LORP and the ASR component, and Dr. June Marecki. She's the lead geologist and geochemist on the project. And similar to Bob Verastro, she also led the ASR pilot studies for the Corps. Today is going to be a full day of presentations from subcontractors, consultants, universities, and staff from other government agencies that have been assisting the district and the Corps with the ASR program to begin addressing these uncertainties with ASR wells that were identified by the National Research Council. After each presentation, we will have approximately 5 minutes for the peer review panel to have a technical discussion and provide comments or ask questions on the specific topic that was presented. And we will also have 2 public comment periods throughout the day. To avoid having panelists speak over one another, we kindly ask that you use the raise hand feature, and we will call on you to provide your comment or question after each presentation. This is our agenda for today, and we are going to try to stick to the designated time frames as we have a lot to cover. There will be 2 public comment periods that I'd like to point out, which is one before noon, and the other one is prior to closing remarks in the later part of the afternoon. The public comment period should be focused or directed to the materials presented and not on the LORP planning effort or on other projects. The 2022 ASR Science Plan report will be released for a 30-day review similar to last year, and stakeholders in the public will have an opportunity to submit comments via email or by letter. Similar to last year's science plan, we will include a comment response matrix on our website for the public to view. If you would like to participate in the public comment period today, we ask that you use the raise hand feature and we will call on you to speak. You will remain muted until you are called upon. Tomorrow's event is only available to the peer review panelists and project team members. We will meet again tomorrow morning, either in person or virtually, for approximately an hour to discuss anything that we may have missed today, followed up by a field visit to an existing ASR well site and an active drilling site where the Corps and the district are installing test exploratory wells. This is the LORP revised recommended plan. The project consists of 55 ASR wells, which are shown in the red circles on the map, and the 2 wetland restoration sites that are shown in green, referred to as the Kissimmee River Center wetland and Paradise Run wetland. The 55 ASR wells are to be installed throughout the watershed. Each cluster may have 2 to 10 wells, depending on aquifer suitability. You may recall that the recommended plan changed from the last time we met with the peer review panel. The above ground storage feature, referred to as the wetland attenuation feature, was removed from the plan due to stakeholder concerns and costs. Although the studies proposed in the 2022 ASR Science Plan are intended to be conducted at ASR locations identified in the 2022 LORP Integrated Project Implementation Report and Environmental Impact Statement, they have broad application beyond LORP scope. As a reminder, these studies have value anywhere ASR wells are proposed within South Florida and can be used to address ASR uncertainties associated with SERP or other SERP projects or non-SERP projects. So over the next few slides, I want to provide a high-level overview of the planning, design, and drilling we performed for the ASR program in the last year or 2. This graphic was included in the 2021 ASR Science Plan and shows that the ASR program is being implemented in a stepwise scientific approach while incorporating the National Research Council's recommendations based on the review of the ASR pilot projects and the ASR regional study. The graphic shows you the steps we are taking to implement and build ASR clusters, such as installing continuous cores, reactivation of existing systems, installing test exploratory wells, wellfield design and permitting, cycle testing, and eventually ASR wellfield expansion. One of the first tasks the project team initiated was reactivation of existing systems. There's an existing ASR well located at the L63 North site, and a mechanical integrity test was performed on this well in 2020. The results indicated that this well is viable and it is going to become part of the well cluster as we expand the L63 North site. Additionally, the project team is currently assessing the Kissimmee River ASR well site and intends to operate the well in 2023 if determined to be cost effective. More recently, the site was used for the proof of concept testing and the project's treatment technology evaluation for the ASR well program. One of the primary steps in building out a cluster is the continuous core step. There are 5 locations where continuous cores are needed since we do not have adequate aquifer data in some of these areas around the lake. The locations are denoted by the gold stars on the map, which include the L63 North, C38 South, L63 South, C40, and C41 clusters. The drilling of continuous cores were initiated in 2020 and will continue into 2023. To date, we have completed the L63 North core, and the C38 South and the L63 South core are currently underway. The continuous core work for the C40 and C41 locations will begin later 2022 or possibly 2023. On the right, you will see what some of the recovered core samples look like. The graphic on the bottom shows you what some of the data looks like that we received, such as water quality data and flow data. And we will go into more detail during the next couple presentations about the findings of the continuous core holes. Prior to drilling at cluster sites, several surveys, studies, and permits are required. For the C38 North and South cluster sites, we have already completed the siting evaluation, conceptual well and wellfield design, threatened and endangered species surveys, constructability analysis, obtained DEP underground injection control or UIC permits for the test exploratory wells, and completed the treatment technology evaluation. On this slide, you will see what some of the drilling activities look like that are ongoing. At both of these cluster sites, we are currently drilling test exploratory wells in both the Upper Floridan Aquifer, referred to as the UFA, and the Avon Park Permeable Zone, which is referred to as the APPZ Aquifer Zone. These wells and their associated monitoring wells are expected to be completed later this year, and the aquifer pumping test will be conducted to determine the capacity of the aquifer and spacing of subsequent ASR wells in these areas. Prior to injecting water into the UFA and APPZ aquifers, the water must be treated to meet regulatory criteria for underground injection control or UIC ASR facilities. The photo on the left was taken in October 2021 during the setup for the proof of concept testing at the existing Kissimmee River ASR well site. A 3-month test was conducted from November 2021 through January 2022. And later on today, we will have a presentation that goes into much more detail about the testing and treatment trains that were run there. The photo on the right shows the color difference between the raw water that's pulled from the C38 canal versus the color of the samples of the water once it has been run through the treatment trains that were tested during our proof of concept testing. The proof of concept testing is complete, and the draft reports of the results were received last month, and we are currently reviewing those results. We are hoping to share the results with the public and the peer review panel later this summer or next fall. The graphic on your left was provided in the Senate Bill 2516 progress report that was prepared in November 2021, and it shows ASR implementation, the different phases, schedule, and estimated costs. Our current plan is to build out 3 ASR well clusters, which is the C38 North, C38 South, and L63 North sites, depending on funding. The colored bars indicate when we will begin our task and not necessarily when we will complete the task. Completion of the task may run over into the following year. Just to give you an idea of the time frame to construct some of these wells, it takes approximately 6 months to drill a continuous core and 2 months to convert it to a monitoring well. It can take up to a year to obtain a permit to install test exploratory wells, and a year or more to drill a well that will be converted to an ASR well for operation in the future. During each of these phases, we are incorporating science plan studies. The yellow bars on the table show when we are implementing studies in the ASR science plan, demonstrating that it will take several years to address these uncertainties. Some of the near-term steps pertaining to drilling, permitting, engineering, and construction are listed on the right side of the slide. This slide summarizes the list of consultants, subcontractors, and types of studies or tasks currently underway for the ASR program that will assist the district and the Corps in addressing ASR uncertainties in the science plan. Like I mentioned before, there will be presentations from Stantec, Florida Gulf Coast University, USGS, Formation, and ECT, where they will highlight their work in scientific studies and go into much more detail about the findings and what it means exactly for the ASR program and the ASR science plan. This is the ASR report card that was included in the 2021 ASR Science Plan, and it has been updated for the draft 2022 ASR Science Plan. The report card shows progress in addressing the National Research Council's recommendations and the ASR peer review panel's recommendations last year. The yellow indicates tasks that were worked on or progress made in 2021, and then the green indicates progress made in 2021 to 2022. The asterisk denotes work progress, such as preparing a scope of work, but hasn't been necessarily executed quite yet and work hasn't begun. The report card update was conducted by district and the core staff and is subject to review and input from the peer review panelists prior to finalization. This year, the project team feels like we have made progress towards investigation in the Avon Park permeable zone through our continuous core process and has begun researching pretreatment technologies to remove arsenic. We have also had analysis of wellfield spacing for recovery efficiency through groundwater modeling and aquifer pump tests to be conducted in the near-term future. We have begun locating clusters near large bodies of water, such as Lake Okeechobee and tributary canals to the lake. On other projects, we are also looking at siting ASR wells near stormwater treatment areas and also flow equalization basins. We have completed our proof of concept testing field event and are considering which treatment technology type will be selected to consistently meet permitting and regulatory requirements. We have initiated or executed work orders for ecological studies such as chronic toxicity testing, long-term ecological monitoring, and a quantitative ecological risk assessment. The project team has completed the ASR Programmatic Quality Assurance Plan, and we will have a presentation about this topic later this afternoon. We have also begun progress towards the data storage and public access, and this is going to be an ongoing task throughout the lifetime of the project. Last time we met with the peer review panel, one of the topics of concern was sharing the data and reports with the public. The yellow arrows on the left of the graphic show the data storage systems that are available for public access. Geology, hydrogeology, and water quality data for the continuous cores and test wells can be found in DB Hydro. As a reminder, DB Hydro was also available last year, but there was not a lot of new data to share with the public at that time. What is new this year is Data 1. Statements of work, permits, presentations, ecological and engineering reports can be found on Data 1, which is currently available to the public. Data 1 is a web-based database that is accessible at the link shown on this slide. Unfortunately, it's not showing up here, but it is also denoted right here in finer print. As I mentioned previously, the subsequent presentations will cover much more detail that will support the ASR program and report card progression. Also, the presentation and recording of today's meeting will be available on our website within a few days following the workshop. Now I'll hand it over to Anna to begin the discussion and introduce the next presenter.
Thank you, Liz. Unfortunately, we don't have any time left for questions at this time. So we are going to move on to our second presentation. And if panel has any questions for Liz, the panel members will be able to ask questions during the panel discussion later during the day. So let's go ahead and let's move on to our second presentation by Hannah Rahman. Hannah works for Stantec and she will give us an update on the ASR continuous scoring program. And with that, I'm going to turn it over to Hannah.
Hi, everyone. Good morning. My name is Hannah Raymond, and I am a hydrogeologist with Stantec. And today I will be discussing the Lake Okeechobee Watershed Restoration Project, Aquifer Storage and Recovery Wells, or ASR wells, the continuous coring program. So kind of before I dive into detail, kind of specifically about the continuous coring program, I wanted to kind of give a brief overview of some other components of the ASR project, because the continuous coring program is because the the continuous coring program is a small kind of component of the overall project. So we are constructing ASR well pairs at all of the sites indicated by the stars on this map. And an ASR well pair consists of a UFA ASR well and an APPZ ASR well. And the purpose of these ASR well pairs are to assist with surface water level stabilization in Lake Okeechobee during the dry periods and the wet periods, and then to assist with wetland restoration in that surrounding Lake Okeechobee area. It is not letting me click to the next slide. Okay. Oh. Okay, so sorry. Okay. I also wanted to go ahead and discuss some of our ongoing work as well as completed work over the last 2.5 years. So as Liz previously mentioned, we did complete a mechanical integrity test on that existing APPZ ASR test well at the L63 North site. We have completed or are currently working on hydrogeologic assessments at the C38 North, C38 South, L63 North, L63 South, C59, C40, and C41 sites. And of course, we have our continuous core holes. We have completed a treatment evaluation. We have also completed a proof of concept for treatment technologies. And then we have also assessed the existing Kissimmee ASR system. This system has been inoperable for about 6 to 7 years. So we have gone ahead and fixed a few of those working parts, and that system should be back up and running once we receive the updated UIC permit. We have also completed C38 North and C38 South ASR test well design and construction documents for our first set of ASR test wells at C38 North and South. Those wells are currently under construction. We are also working on the L63 North ASR test well design and construction documents for the L63 North site. And those documents should be advertised very shortly within the next few weeks. And then we also have an upcoming groundwater model. So this is a picture of the C38 North site. So we have 2 drill rigs at the North site and then 2 drill rigs at the C38 South site. And we are simultaneously constructing 2 UFA wells and 2 APPZ ASR test wells. We are currently permitting that second set of wells, and these are anticipated to start in late summer 2022 or more towards the end of the year. So I am now going to talk specifically about the continuous coring program, and the bulk of this presentation will be about the L63 North continuous core hole. I did want to mention that kind of the main purpose of the continuous coring program is to assist in the design and construction of those ASR test wells. So currently there are 5 continuous core sites. We have the L63 North site right here located to the north of Lake Okeechobee. The site has been completed. We have our C38 South site, which is currently in progress. We began coring here last year. We have our L63 South site located right here, and this site is also in progress. We began coring here just a few months ago. And then lastly, we have C40 and C41 right down here, and both of these sites are in that kind of initial hydrogeologic investigation phase, and they are scheduled to begin either at the end of 2022 or early 2023. So taking a closer look at the L63 North site, there are 3 existing wells. We have the L63 North APPZ ASR test well right here, an existing UFA monitoring well, and then an existing dual zone monitoring well right here. And then this blue star, that is indicating our L63 North continuous core hole, and this core hole has been successfully plugged and abandoned. So I'm now going to go into a bit more detail about what the continuous coring process entails. So we begin collecting cuttings from land surface to 500 feet using the mud rotary drilling method. Once we reach 500 feet, we switch over to the wireline coring method and begin collecting 10-foot cores that are 2.5 inches in diameter to 2,000 feet below land surface. The reason for collecting cores from the reason for only beginning to collect cores at 500 feet is because we want to ensure that we capture that Hawthorne-Swanee contact. And then we only core until we reach the base of the Hawthorne and the top of the UFA. And once we reach that contact, we begin our Packer testing. And so at this site, that contact occurred at 700 feet. And so at 700 feet, we began alternating between coring and Packer testing. Our Packer tests are conducted every 30 feet, and they are off-bottom Packer tests. And in regards to the Packer test, we collect field water quality throughout the duration of the Packer test. We want to ensure that our water quality parameters have stabilized. And so once the water quality has stabilized and our Packer tests are deemed complete, we collect one final water quality reading, and then we collect additional samples to be sent to the lab for further analysis. We also collect isotope samples, and then we take our field data from each Packer test, and we are able to calculate out a specific capacity. Going back to the cores, I did want to mention that we do calculate a recovery percentage for each 10-foot core, as well as we calculate an RQD, which stands for rock quality designation. And this RQD just gives us a better idea of the degree of fracturing that is occurring in the confining units and the aquifer. And then that last kind of major component of the continuous coring program is geophysical logging, which does include an OBI log or optical borehole imager log, and this is performed by the USGS. So here are some cores. These are specific to L63 North. So this first core right here, this is a core taken from the Hawthorne. As you can see, it's very green in color and very clay, both indicative of the Hawthorne. This middle picture right here, this is showing that Hawthorne-Swanee contact identified at 697 feet. This last core over here is showing that that Swanee-Ocala contact right here at 708 feet. And then this core right here, this is a core taken from that Ocala limestone. And it's kind of hard to see in the picture, but this core is quite abundant with an Ocala index fossil known as the Lepidocyclina ocalana. And this particular Ocala index fossil was quite prominent throughout the entire Ocala limestone. This middle picture is showing that Ocala Avon Park contact identified at 1,300 feet. And then this last core right here, this is a core taken from the Oldsmar Formation. And I just wanted to show kind of that transition from a very dark billowstone into a very white gypsum. So taking a look at some fossils and features specific to the L63 North site, we have a lemon shark tooth. This was identified in the Hawthorne. We have a phosphate nodule. This was also identified in the Hawthorne. Here are some spun spicules, and these were identified in that Swanee limestone. Here is that Ocala index fossil. Again, this time I have it under microscope just to kind of give a better view of what they look like. And then here are some pyrite veins, and these were also identified in that Ocala limestone. Here is a picture of some limestone with grains comprised of mudstone rip-up clast. These were also identified in that Ocala. And then here is a picture of glauconite, also identified in the Ocala. And these two features, these were both identified in that Avon Park formation. So we have a bryozoan calcite precipitation infill right here, and then a gypsum crystal right here. Both of these are under microscope. And then this is probably the most interesting layer that was identified at the L63 North site. This has tentatively been identified as an ash layer found at 1,466 feet. And I did want to mention that we had originally identified this as some type of silica sand layer. However, this particular core was sent to Florida Gulf Coast University for some additional analysis by a few of their graduate students there. And they have tentatively identified it as an ash layer. And this ash layer potentially comes from an impact event 36 million years ago, possibly the Chesapeake Bay impact crater, where a bolide impacted the eastern shore of North America in the late Eocene. and it is actually one of the best preserved wet impact craters in the world. So we also sent 8 collected core samples to Mineralogy Inc., which is a lab out of Tulsa, Oklahoma. And for further detailed analysis, this detailed analysis included using a scanning electron microscope, X-ray diffraction, and thin section analysis. And these reports came back full of information. And so I quickly just wanted to kind of point out a few interesting things in that report. So the first is this pyrite flamboyant illite identified at 697 feet. The second, we have a calcareous algae plate and some 4M skeletal fragments identified between 1,154 to 1,155 feet. And then lastly, over here, we have some authogenic dolomite with intercrystalline porosity and possibly some microcrystalline pyrite. Moving on to our packer testing. So as I mentioned, we completed off-bottom packer tests every 30 feet. And the majority of the packer tests were performed using a flow rate of approximately 30 gallons per minute. So over here, I have our specific capacity results from each packer test, graph versus depth. And then over here are the water quality analysis from each packer test, graph versus depth. And using both of these data sets, we were able to identify that UFA, the upper flood and aquifer flow zone, between 700 and 800 feet. As you can see, there's an increase in specific capacity and a change in water quality. We also identified 2 flow zones. In the APPZ, we have the Avon Park Permeable Zone APPZ Flow Zone 1 between 1,300 to 1,450 feet. Again, we're seeing an increase in specific capacity, indicating greater flow, and then a change in water quality. And then we identified that APPZ flow zone 2, or that lower flow zone, between 1,510 to 1,630 feet. Again, a fairly large increase in specific capacity here and a change in water quality. And then we also identified the upper interval of that lower flood and aquifer, or LFA flow zone. We did not identify the base of it because we did not core past 2,000 feet. We also, and so you can see there's a change in there's an increase in specific capacity and an increase or a change in water quality right there. And then with this, we were also able to identify that 10,000 milligrams per liter TDS interface. And so taking a look at our water quality. So here is, so this is the orange line. This is indicating that 10,000 milligrams per liter TDS interface. And taking a look at our TDS at about 1,870, that is where that TDS is consistently above 10,000 milligrams per liter. And then to further support this and to get a better, more clear idea of what our true water quality looks like, we produced a log-derived TDS graph, which is right here. And again, looking at this, at that about that same depth, 1,870, that is where our TDS is consistently above 10,000 milligrams per liter. So therefore, at this site, at 10,000 milligrams per liter, TDS interface was identified at 1,870 feet. We also completed a series of octasolve analysis on each packer test interval. We used 3 industry standard analytical methods for confined aquifers. And so this included Tice recovery, Cooper, Jacob. And then we also used the Driscoll empirical equation to kind of get a 4th transmissivity value. And so we then averaged our 4 results together to get an overall estimated average transmissivity for each packer test interval. And then we took that result and divided that by our packer test interval, which was 30 feet. And we were able to calculate out an average estimated hydraulic conductivity. And so I have this, this table color coded. So the blue is indicating our flow zones and that green is indicating our confining units. And so taking a look at our flow zones, that transmissivity and the hydraulic conductivity have much higher values as compared to the confining units. And then down here, this is our APPZ flow zone 1 and our APPZ flow zone 2. And there's actually a semi-confining unit right in between those 2 flow zones. And if we take a look at the transmissivity and hydraulic conductivity values, those values are slightly higher in the semi-confining unit as compared to the confining unit, which is what we would expect to see.
5 minutes.
So moving on to our isotope analysis. We send our isotope analysis to the University of Arizona's Environmental Isotope Lab for oxygen and deuterium analysis using a gas source ratio mass spectrometer. And so this is showing all of our data. The blue dots are our isotope data, and then this black square right here, this is actually a sample from the L63 North Canal. And we sampled this for comparison purposes because we wanted to ensure that there was no mixing between the canal water and groundwater during our drilling processes, which there was not. This thick black line right here, this is that global meteoric water line. And then this thin line right here, that is that Florida evaporation trend line. So if we separate our data by aquifers and confining units, we see a very clear pattern. So I will go ahead and start with the aquifers. So here is just the aquifer data. The red dots are denoting that UFA. The green dots are denoting that APPZ. And then those purple dots are denoting that lower Florida aquifer. Taking a look, that UFA and the LFA have very distinct signatures. Our UFA is showing much lighter isotopic signatures trending toward freshwater values, whereas that LFA is showing much heavier isotopic signatures with values trending toward ocean water. And I have ocean water denoted on this graph by that blue triangle, and that sits right here at 0, 0. And so our confining units show a very similar pattern. So here, the red triangles are denoting that MC1, or middle confining unit 1. The green triangles are denoting that semi-confining unit. And then those purple triangles are denoting that MCU2, or middle confining unit 2. And so that MC1 is showing isotopic signatures between that UFA and that APPZ. That middle confining unit 2 is showing isotopic signatures right there between that APPZ and that LFA. And then our semi-confining unit is showing isotopic signatures right there in between those two APPZ flow zones. And this is a figure just to kind of summarize up the isotope analysis. So on this graph, I have oxygen and deuterium graph versus depth. And this just further supports that with depth, we are seeing values trending toward ocean water, and they are having heavier isotopic signatures. Moving on to geophysical logging, we completed a series of geophysical logging suites on the open core hole. So this included an XY caliper and gamma ray log, a flow meter log, a borehole compensated sonic log, and then a dual induction with variable density log, and that OBI log that I mentioned earlier. So here is a figure that not only shows our geophysical logging results, but it shows our hydrogeology and geology interpretation in PICS. It shows our water quality data from each packer test, as well as our specific capacity results and the existing ASR, UFA, and dual zone monitoring well open hole intervals. And so our geophysical logs coincide really, really well with our upper flow zones and our formations. And so this kind of just further supports what we are seeing in the field. Here are some screenshots from that OBI log, and I wanted to point out that this OBI log does further support where we are seeing those flow zones. So from 700 to 740, that is that upper interval of that UFA, where we saw an increase in specific capacity indicating flow. And here we are seeing quite a bit more fracturing, dissolution, and higher porosity, again, all indicating flow. And similarly here, from 1300 to 1360, that is right there in that upper interval of that APPZ, where we saw a pretty large increase in specific capacity. And here we are seeing quite a bit more fracturing, again, higher dissolution and more porosity, all indicating flow. So to summarize up the L63 North site, it has been recommended that the future UFA ASR test will have an open hole or injection zone interval between 700 and 900 feet. And then the future APPZ ASR test will have an open hole or injection zone monitoring interval between 1,300 to 1,450 feet. And so this figure just shows well construction details, as well as some additional coring and packer testing that we'll be doing. And then we will also be completing pumping tests on these wells once they are constructed. So if we move about 7.5 miles to the southwest, we reach our second continuous core hole site, C38 South. And this site does differ a bit from L63 North, mainly because it is under a UIC permit. And so this just means that we have to submit weekly construction documents and a weekly construction report to the FAEP, as well as submit a casing seat request. And we have to receive approval on that before we can install casing at this site. The other main difference is the C38 South core hole will be constructed as an APPZ monitoring well, and that will be done simultaneously. We will be constructing that APPZ monitoring well simultaneously to core and impactor testing, whereas at L63 North, we solely core and impactor tested to 2,000 feet, and then we're going to go back and construct those ASR test wells. Taking a look at some cores specific to C38 South, this first core right here, this is showing that Hawthorne-Swanee contact identified at 536 feet. This middle picture is showing that Swanee-Ocala contact identified at 552 feet. And it's kind of hard to see, but there is actually a direct straight line where that contact occurred. This last picture right here, this is another core taken from that Ocala limestone. This core picture right here, this is showing that Ocala Avon Park contact identified at 1,242 feet. And then this middle picture is actually showing that transition into that Avon Park formation into that APPZ. And that contact was identified at 1,376. So we go from a very light colored limestone into a darker colored Yellowstone.
1 minute.
And then this last core picture right here, this is a core taken from that APPZ. Taking a look at some fossils and features specific to C38 South, we have a bryozoan fossil. This was identified in the Hawthorne. Here is an oyster shell also identified in the Hawthorne. And then here's that Ocala index fossil. We have a sand dollar mold also identified in the Ocala. And then here is another very common Ocala index fossil, the Ligopygus species. And this particular Ocala index fossil was prominent at both C38 South and the L63 North core hole. And then we have some possible lignite right here. Again, these graphs probably look very familiar. Again, I have the specific capacity results from each packer test, graph versus depth, and then our water quality results, the graph versus depth as well. And we were able to use these data sets to identify that UFA right up in here, where we see that increase in specific capacity and change in water quality. And then that upper interval of that APPZ, kind of right where we hit that contact, we're seeing that increase in specific capacity and a change in water quality. So here is a generalized hydrostratigraphic section illustrating all of our data to date at the C38 South site. And with this figure, I kind of just wanted to kind of acknowledge that we are seeing the same geophysical logging signatures at the C38 South core hole as we're seeing at the L63 North core hole, and as we're seeing at both the C38 North and C38 South ASR test wells. The only main difference is that we're seeing is that Hawthorne UFA contact at C38 South core hole, that contact was identified at 536 feet, whereas at that L63 North core hole, that Hawthorne UFA contact was identified at 700 feet. So at C38 South, that contact was identified 160 feet shallower than at L63 North. And that is kind of one of the main reasons we are putting in these test borings, is because we want to understand and see that variability in the hydrogeologic conditions between the different sites. Here is a figure depicting our current APPZ monitoring well construction details for the C38 South core hole. So we are in the process of installing 6.625-inch outside diameter fiberglass reinforced plastic casing to 1,350 feet. And the purpose for installing this casing to that depth is we want to ensure that we isolate that UFA from that APPZ. And so once we get this casing installed and cemented to ground surface, we will trip back in with our coring barrel and bit and resume coring and packer testing to 2,000 feet. And then last but not least, the L63 South site, located right here. As I mentioned earlier, we did begin coring here just a few months ago. And so far we have cored to 660 feet, and we have identified that Hawthorne UFA contact at 630 feet. So again, we are seeing variability in that contact just between these three sites. And this core hole will be constructed as a dual zone monitoring well. And then the last thing I wanted to quickly mention or show are these fossils. We believe these are star corals, and these were identified right there at that Hawthorne-Swanee contact. And that's it. Thank you.
Thank you, Hannah. So we have about 2 minutes left for the panel discussion session. Reminder for our panelists, please use raise your hand feature in Zoom, and Liz will call your name in the order the hands were raised. Any questions for Hannah?
And Anna, I don't see any hands raised at this moment.
Okay, thank you, Liz. In this case, we will move on to our third presentation by Dr. Jamie Mcdonald. And Jamie is a professor of geology at Florida Gulf Coast University. And today he will give us an update on the geochemical analysis of the L63 North continuous core. Jamie, are you ready?
I'm ready.
All right.
Can you hear me okay?
Yes.
Okay, great. And then when I'm ready to move on to the next slide, I'll just say, next slide, please, or something like that. Like Anna said, I'm Jamie Mcdonald, a professor of geology at Florida Gulf Coast University. My colleagues working on this project with me were Dr. Rachel Roach. She's an assistant professor of hydrogeology. Dr. Chu Cho, who is a professor of chemistry. And then we had 4 undergraduate students who are all environmental geology majors: Richard Molina, Zoe, Sophia Moron, and Rachel Walter. We also had tremendous assistance from the NED from the district, who helped us make some wonderful graphs. I wanted to mention that at the beginning here. Okay, next slide, please. So, as I'm sure everybody aware who's watching these presentations, aquifer storage and recovery has been shown to potentially mobilize metal elements from carbonate rocks in Florida aquifers. And this is a very classic study from Arthur, where arsenic and uranium were mobilized during cycle tests up in Hillsborough County. And so this has been known for a while, and it's of concern. So what we wanted to do was we wanted to identify, well, we want to do several things. Next slide, please. We wanted to chemically analyze the core from L63N to find areas of potentially high metal concentrations using a handheld, or more oftenly called a portable X-ray fluorescence. So if I say XRF during this presentation, it means X-ray fluorescence. This is an instrument that's very commonly used for geochemical analysis, X-ray fluorescence. A portable X-ray fluorescence, or a handheld X-ray fluorescence, is becoming more and more commonly used. Because it rapidly analyzes rock, and it also has very high accuracy and precision, as we'll see. Our goal was to take one analysis every foot of the roughly 1,500 feet of core from L63N. And then we did, sorry, I'm talking in the past tense, we did concentrate additional analysis on areas of interest. Next slide, please. The intent was to find any areas of concern where metals might be unusually high. And so we utilized the X550 from a company called SciAps. It's a very robust instrument. All handheld XRFs operate on multiple settings to correct for overlaps and elements. Any analytical instrument that uses X-ray fluorescence does this. This instrument uses 2 different settings. It has a soil setting that has 3 different channels that runs on 3 different kilovolts and microamps to minimize elemental overlap. And the soil setting is designed for low concentration elements. Then it has what's called a mining setting for what I'm referring to as major elements, but these are elements that occur in the rock at much higher concentrations. And the mining setting has 2 different channels that operate at 2 different kilovolts and microamps, again, to minimize elemental overlap. And so the instrument takes a large number of analyses all at once on multiple channels, but you run the soil channel and then you finish that analysis, then you can run the mining channel. So next slide, please. The instrument comes internally calibrated from and standardized from SciAps. And these are just 3 examples of the internal calibrations for your reference. We worked with the company SciAps to help modify calibration curves and add calibration curves so we can make sure we were covering all the elements of interest for this study. The one thing I'll point out is these are just 3 internal calibration curves for the instrument. You'll see in the center one, that's for mercury, the one on the left is for molybdenum, and the one on the right is for lead. The one in the center has those 2 analyses that are much higher on the upper left-hand corner of the graph. Those were excluded from the calibration curves. That's one of the things we did. We worked with the company to maximize the efficiency of these calibration curves and to make sure they were as accurate as possible. And then we added elements too that we needed for analysis in this study. Next slide, please. So we had several things that we needed to do. The picture on the left there is showing the core as we received it. And you can see it's pretty crusty. It's got crud on the surface of it. And it's rusted too. Part of the core retrieval process causes rust to form the outside of the core. And so we did several things to prepare the samples that were quite simple. We just cleaned the sample off using a wire brush. And so the picture on the right shows the after of the cleaned off core, where with a sort of gentle rubbing with a wire brush, we were able to remove any debris or rust that's along the core surface, because we didn't want that to interfere with our chemical analysis. The instrument takes its chemical analysis by placing the X-ray fluorescence right on the surface of the sample. The XRF, or X-ray fluorescence instrument, needs continuous contact with the sample. And so we 3D printed a curved adapter piece so that it would sit very snug on the curved core surface, and that worked very well. Based on several recommendations of peer-reviewed published studies using handheld XRF, we made sure we had a smooth surface that was free of voids. The sample needed to be relatively intact and needed to be a thickness that's about half the core width. And the sample needed to be dry. A wet sample will mute the intensity of the X-rays entering the sample. And so you'll get an underreported value if the sample is wet. And so the thing that was most cumbersome to overcome, it took the longest amount of time, was drying the core. So we dried the core out on tables using fans. The core sat inside an air-conditioned building for several months. But even after several months, some of the core boxes which had been closed still had pore water escaping from them. And so we had to make sure the sample was very dry or dry before we analyzed it. Next slide, please. So these are the elements that we measured. There's Zoe measuring a core box. You can see the wire brush sitting next to the core box, and she has the handheld X-ray fluorescence instrument touching the core. Excuse me, I'm sorry. With the soil setting, we measured most of our quote unquote trace elements, specifically elements that we were focused in on were arsenic, copper, cadmium, mercury, molybdenum, lead, and uranium. But then we analyzed these other elements too: sodium, titanium, vanadium, chromium, cobalt, etc. Then the elements we analyzed with the mining setting were things like aluminum, silicon, phosphorus, sulfur, potassium, calcium, manganese, magnesium, and iron. And so we analyzed a large suite of elements very quickly. It took about about a minute for the soil and about 45 seconds for the mining analysis. So not only could we get a large number of analyses, but we could get them quite quickly. The next slide, please. I'll just move on. We wanted to test the instrument's precision and accuracy. And so in order to test the accuracy, we analyzed 9 samples from the core multiple times. Some of them we analyzed twice, but a couple of them we analyzed more than 2 times. So here you'll see several graphs. I apologize, the graphs are kind of small. I should have just maybe used less graphs. Here you see several graphs showing the linear relationship between those run 1 and run 2. Run 1 was the first time they were analyzed, and run 2 was the second time they were analyzed. The slopes and the y-intercepts are quite small, which is the slopes are close to 1 and the y-intercepts are close to 0, which is what you want for accuracy. One example, though, is sulfur's slope was 0.66. It's a little hard to see this. Sulfur's the bottom left-hand graph because the graphs are small, I apologize. But there's one outlier from the sulfur. And if you remove that one outlier from the sulfur, its slope increases from 0.66 to 0.96. And so, same thing happens for molybdenum. If you remove the one outlier from molybdenum that's off of the slope, that slope greatly decreases from 1.5 to close to 1.1, which is an acceptable value for a slope for an X-ray fluorescence that's handheld. Next slide, please. We calculated both the correlation coefficients, and not shown on this graph, but we did the relative standard deviation too. For a handheld XRF, a quality analysis should have a correlation coefficient of about 0.95. And it should have a relative standard deviation of less than 20%. All of our analyses had correlation coefficients, all of our elements based on these multiple runs had correlation coefficients of greater than 0.95, except for calcium, which was 0.94, which is within an area of acceptance. And then the relative standard deviation for all of these elements through the multiple runs was much less than 20%. This showed that we could get the same answer over and over again. So our accuracy was quite good. So now we needed to test the precision to make sure we're getting the right answer over and over and over again. And so next slide, please. And I apologize, there's no graph on here, but this just says that we use 4 standards from the Geochemical Society of Japan. And these are standards that any national or international lab acquires to also test the accuracy and precision of their instruments. So this is to test our precision. We analyzed these standards multiple times using both soil and mining settings. So we did it at least 3 times with mining and at least 3 times with soil each. We then calculated the averages and then looked at the error and standard error percentage, as well as standard deviation and standard deviation percentage for these elements away from which are the expected values. All of them were within 10% of the standards, all of the elements, which was great, except for several, specifically cadmium, mercury, and phosphorus, which are of concern to us, and silver. To correct for these elements, we used a linear equation where y equals f times x. Y is the known value that we were supposed to get, and x is our measured value. So therefore, f becomes our correction factor. We generated this by dividing the known value divided by our measured value. So an example for silver is the known value should have been 1.04. Our measured value was 35. And so we had to correct our analysis for silver down by 0.0297. This is a very typical correction that's done by national labs and international labs. And when we corrected our analysis for magnesium, we got the expected magnesium values that we should get, and for phosphorus and for cadmium. And so, we were able to show that this instrument accurately measures and does good precision too. So this is a tremendous instrument to utilize in order to analyze the cores. And now that we know it's a good instrument to analyze the cores, let's analyze the cores. Next slide, please. And so here are some of the 1,339 analyses from core N63. We actually took 1,436 analyses, which is very impressive. And remember, every one of those analyses is twice, once for soil and once for mining. But 98 of the analyses gave bad totals. Either the totals were too low for a carbonate rock or too high for a carbonate rock. And so we removed 98 of the samples as a quality control measurement, and we only focused in on the 1,339 samples that gave values and total amount of elements within the expected total amount of elements you would have for a carbonate rock. And so here are just 3 graphs: calcium, magnesium, and silicon as a percentage that the NAD very graciously generated for us with our data. And you can see some trends and a running average for the samples as you go from the top of the core at 500 feet to the bottom of the core around 2,000 feet. The gray box between 700 and 800 feet, that's the upper Floridan aquifer. The gray box between 1,300 and 1,450 feet, that's the Avon Park permeable zone. And then that thin dashed line is this high silica content or ash layer at 1,466 feet. You can see generally calcium starts off quite low and then increases, but then decreases again around 1,300 feet. Magnesium starts off low, but then increases and then decreases sharply around 700 feet, stays low until about 1,300 feet where it increases and then stays high for the rest of the core. Silicon starts off very high in the confining units and then drops off markedly at 700 feet and then stays quite low for the rest of the core. You see several spikes in silica at greater depths. One of those spikes, the highest spike, is related to the 1,466-foot section of core, but the other ones are going to be related to organic layers that we'll see in a second. Next slide, please. Here are for aluminum, iron, and titanium. Titanium's in parts per million, where aluminum and iron are in weight percent. The other elements on the first slide were in weight percent too. You'll see a marked decrease of aluminum from the top of the core. Then at around 700 feet, it gets very low and stays relatively low. Iron does something very similar. It's high at the top of the core, and then around 700 feet, it gets low and stays relatively low. And then titanium does the same thing too. Titanium is high at the top of the core and then gets low around 700 feet, stays relatively low. You'll see spikes in aluminum, spikes in iron, and spikes in titanium below their average deeper in the core. Many of these spikes are associated with organic layers that we're going to focus in on in a few slides. Again, this transition from higher to lower aluminum, iron, and titanium are occurring right at 700 feet, which is you're coming out of the confining units, which have a lot of clay in them, into the more pure carbonate rocks, which would expectedly have low aluminum, iron, and titanium in them. Next slide, please. Here are some of the metals that we wanted to focus in on. Arsenic, copper, and molybdenum. As you can tell, there are far fewer analyses of these metals than of the other elements. The elements on the first few slides are considered major elements that are very common in rocks. These are trace elements that are less common. And many of the analyses were either at or below the detection limit for the instrument, which for arsenic is, I believe, 1 part per million for the instrument. Hold on, let me confirm that. I got it right here. Oh, I should have been ready. Oh, don't hold this against me. Here it is. Arsenic is 1 part per million. Copper is 3 parts per million, and molybdenum is 1 part per million. And so you can see how these are semi-logarithmic scales. You can see molybdenum's in a percentage, but copper and arsenic are in parts per million. You can see that there's fewer analyses of arsenic. Only 12% of the entire core had measurable arsenic in it. Only 26% of the entire core had measurable copper in it, and only 65% of the entire core had measurable molybdenum in it. One of the things that's also noticeable is it's more common to have arsenic, copper, and molybdenum occurring within the measurements at the top of the core, because the confining units, again, have a lot of clay in them, and these clays tend to have more of these metals in them than other elements. Again, the gray boxes, the upper gray box is the upper Florida aquifer, the UFA. The lower gray box is the Avon Park permeable zone, the APPZ, and then that dotted line is the layer of interest at 1466. The one thing you should notice here is at the top of the APPZ, the top of the Avon Park permeable zone, so the lower gray box, the metals are high for all of them. Arsenic is high, copper is high, molybdenum is high. And we're going to focus in on this in a second. Next slide, please. And then here's mercury, chromium, and nickel. Mercury occurred in about 88% of the analyses. Mercury was quite robust in the core. And again, you can see there's a spike at the top of the Avon Park permeable zone for mercury. And there are a bunch of spikes for chromium. There's not very many chromium analyses, and a bunch of spikes for nickels also throughout the core. And again, these are going to be associated, many of these spikes below 950 feet are associated with what we're going to call organic layers in a second. The one thing I do, Liz, could you please go back? Thank you. The one thing I do want to focus in on, and I did mention it before, is molybdenum tends to be a little high in the upper Floridan aquifer, and nickel tends to be a little high in the upper Floridan aquifer compared to other trace metals, which are near average or below average in the upper Floridan, average for the entire length of the core. Okay, next slide. Thank you, Liz. So here's the focus in on the upper Floridan aquifer, or the UFA. Here I'm only showing molybdenum, mercury, and nickel. I'm not showing a graph for arsenic because arsenic is about 8.5 times lower through this interval of the core than its average value for the entire length of the core. So on average, arsenic is lower through this 700 to 800 foot zone. Molybdenum is about average for this length of the core.
5 minutes.
Okay, thank you. Molybdenum is about average for this length of the core, and nickel is again about average for this segment of the core. What's not shown is vanadium. Vanadium tends to be a little bit higher. It's about 1.9 times, almost 2 times higher through the 700 to 800 foot interval of the core than the average value from vanadium for the entire length of the core. But mercury is low. Mercury is about 1.3 times lower on average, and arsenic is very low through this section. Next slide, please. Here's a focus in on the Avon Park permeable zone. On average, the trace metals are higher in the Avon Park permeable zone than they are through the upper Floridan aquifer zone. So from this 1,300 foot to 1,450 foot interval, the trace metals are generally higher. And you'll also see on the left of each of these graphs for molybdenum, mercury, and nickel, there's a spike in the metals. And this is consistent. Almost all of the metals we measured have a higher value right at that 1,300 foot interval, and then they decrease, but still remain generally higher through the Avon Park permeable zone than the upper Floridan aquifer for the length of the Avon Park permeable zone. If that makes any sense. Next slide, please. We were able to utilize this data for other things besides finding areas where metal concentrations may be high or low, relatively speaking. So for example, the aluminum calcium ratio of the core can show us that transition from the confining units into the lower carbonates. And so there's a big drop off between the aluminum calcium ratio at around 700 feet, which is where we have the contact between the confining units and the lower carbonate rock. Next slide, please. So we took 232 of the analyses from the from the confining units, and we looked at their potassium aluminum and iron aluminum ratios, and then we compared them to the known values for clay M members, for kaolinite, vermiculite, illite, and montmorillonite, which is a smectite. And the chemistry generally suggests that these clays in the confining unit are a mixture between illite and montmorillonite. This was also displayed by X-ray diffraction from Mineralogy Incorporated that found they had schmectite, montmorillonite to schmectite, and they had a large amount of illite than when they did their XRD analyses. And so the clays are a mixture between probably illite and montmorillonite, and the chemistry is supporting that. Next slide, please. We can also use major element ratios to identify facies changes. So not only does the aluminum calcium ratio show that facies change between the confining units and the lower units, but so does silica and calcium. The magnesium calcium ratio can show that magnesium is very commonly found in clays, and then it falls off at 700 feet. But then at 1,300 feet, there's a marked increase in the magnesium calcium ratio up to 0.8 or sometimes close to 1. The average value for dolostones should be around 0.8. And so you can see this facies change in the rocks. You also see a couple of spikes in the magnesium calcium ratio at around 960 to about 1,100, 1,200 feet. Those are probably dolomitic layers within the Ocala limestone, within the limestones that are found through that interval. Next slide, please. We were also able to utilize the major element ratios to look at the nodular massive gypsum that forms down the Avon Park Formation. The diagram on the left is a Raman spectrometer analysis of the gypsum, and each of those peaks represent strengths of a bond. Raman intensity basically works the same way X-ray diffraction works. And so I took 2 samples and I analyzed them by the Raman laser, and I got a greater than 97% match that it was gypsum, so it's not some other sulfate. Next slide, please.
One minute.
You can see here that the sulfur calcium ratios are similar through this interval, what you would expect for gypsum. Next slide, please. We analyzed several organic layers. Next slide, please. Most of these organic layers are between 956 and 1958 feet. And the metals in these organic layers are quite high. Arsenic is 10 times higher on average in these organic layers than the length of the core. Molybdenum is 13.7 times higher in these organic layers than the average value from molybdenum for the core. Mercury is about 5 times higher, or 4.8 times higher in these organic layers. The nice thing, though, is the organic layers are deep in the core, and none of these organic layers occur within any flow zones that have been identified. So the organic layers don't occur within the upper Floridan aquifer, they're much lower than that. And they don't occur within the 1300 to 1450 interval through the Avon Park permeable zone. But they're areas of concern that have much higher metals than other areas within the core. Next slide, please. And then here's our friend, our 1466-foot depth core interval. This is a really special little segment of the core. It has potential for great impact. It has very high silica calcium ratios, very high sulfur calcium ratios, strontium calcium ratios, aluminum calcium ratios, phosphorus calcium ratios, and molybdenum calcium ratios compared to the 4 or 5 feet above and below it. Above and below it, it's laminated dolostones. Then within this sort of 4 to 5 inch section of the core, it's a very highly disrupted, very sulfur rich area that smells strongly of sulfur. The magnesium and calcium are greatly diluted in this area too. It no longer has a ratio where you can consider it a dolostone. So the depositional setting is getting washed out by something. The Avon Park formation is Middle Eocene, but that's a relative age based on fossils. There's no absolute ages from the Avon Park formation. So this is a potential marker bed. And also it could be something that could give us an absolute age. Clearly it's some sort of high silica ash contents coming in from someplace else. There are Eocene volcanic eruptions occurring within the Caribbean and within the Appalachians of North America, believe it or not, up in Virginia during the Eocene. Those are around 45 million years old, 45 to 42. But then there's also the Chesapeake Bay meteorite impact structure at 35 million years old. And so getting an absolute age out of this layer could help confine not only the age of the Avon Park formation, but also how this occurred. Is this a volcanic eruption layer from a very large volcanic eruption, or is it something more amazing, like a meteorite impact from the Chesapeake Bay meteorite impact structure? You can find tektites within the Gulf of Mexico and in the Caribbean that are Eocene age, buried within recovered cores from International Drilling Project. Final slide, please. This next slide. Next slide, please. One there. Thank you. So I apologize. I was rushing towards the end. I didn't think I would take that long. So generally speaking, we have demonstrated that a handheld XRF can rapidly and accurately and precisely measure hundreds, thousands of analyses within a core sample from the ASR project. And it can be utilized to find areas of concern. That ash layer is an area of concern. It should be avoided because the metal concentrations are very high. The organic layers are areas of concern because their metal concentration is very high. The nice thing about this, though, is that ash layer and those organic layers, none of them occur within the flow zones. None of them occur within the upper Floridan aquifer or the APPZ. Generally speaking, the upper Floridan aquifer, that 700, 800 foot interval, has generally lower metal concentrations than the Avon Park permeable zone. And that's it.
Thank you, Jamie.
Sure, I'm sorry I was rushing towards the end.
That's okay. Thank you, Jamie. And now we have about 2 minutes left for the panel discussion session. Any questions for Jamie?
I see something typed into the
Doc-
question and answer.
Actually, we'll let the panelists discuss. So I see
Okay,
that
thank
Dr. Renee Price has her hand raised.
Oh,
Do you want to go
good.
ahead and
Good.
say your comment or question?
Oh, please go ahead, Renee.
Sure, Jamie. That was a really, really interesting presentation. Thank you very much.
Sure.
My question was about when you were doing the accuracy and precision analysis, and some of the elements had intercepts that were not at 0.
Right.
And I'm just wondering if you can explain how that happens.
You have a variability in the core when you're analyzing the sample. We're analyzing the surface, and it analyzes down to about 2 centimeters. And so you're getting sort of a general analysis for an area, not a single point. And so you have to take that into consideration first. The second thing is published data for handheld XRF analyses will allow a variance in the y-intercept from 0.9 to 1.1. And so our y-intercepts for almost all our elements are within that variation range that's acceptable for really any X-ray fluorescence. Then we can, so our y-intercept is just one of many things we utilize. So we did y-intercept, we did slope, we also did correlation coefficient, and we also did relative standard deviation. And so if an element had a bad y-intercept, but it might have very acceptable correlation coefficients and relative standard deviations, and bad as in it's 0.12 instead of 0.11 or something like that. And so none of them were so egregious that you would want to remove them outright. And then several other researchers suggested that a variation in y-intercept of up to 5% is acceptable based on the standard and precision of the instrument. And so they weren't perfect, but they were well within accepted rates that you would get from published studies. Renee, is that answering your question?
Yes, it was great. Thank you.
Oh, you're welcome. And again, the y-intercept was just one of multiple approaches we took to make sure our accuracy was good and precision was done with standards. The y-intercept was only generated from repeat analyses. One basic limitation, though, of the repeat analyses is if we picked a place on the core that maybe it didn't have any nickel present, we just, we couldn't get a nice repeat analysis on nickel. So maybe we only measured nickel in 4 of the 9 or something like that. So we worked with the data we had. And that's a good thing, though. It just means nickel is very low on the sample and wasn't being detected by the instrument.
Great, thank you.
No, you're welcome.
And Anna, I do not see any other hands raised.
Okay, thank you, Liz.
Okay.
So now we are going to take a short break, and we will be back at 10:30 a.m. sharp. Thank you, everyone. Welcome back, everyone. It is 10:30 a.m. and now we will move on to our next presenter, Victor Flores, who is a researcher and analyst at the U.S. Geological Survey in Davie, Florida. And today, Victor will give a presentation on the multi-well assessment of fracture porosity of the Floridan aquifer system. And now I will turn it over to Victor. Go ahead, Victor.
Hello, good morning. I couldn't find the unmute button. I finally did. Can you guys hear me?
Yes, we can.
Oh, okay, excellent. So it worked. Yes, my name is Victor Flores. I am a Cherokee Nation contractor working for the USGS office at the Davis Research Center. And today I will be presenting our approach. Oh, I believe I had to request the controller, right? For the presentation. Let me see. Okay. Okay, so as I was saying, I will be presenting our approach to assess the fracture porosity observed on the ASR wells that were discussed a second ago. I think we lost the connection. I don't see anything on the screen for now.
Any technical difficulties? Maybe I can run the slides.
Yeah, but can you see anything on the screen?
No. Can you stop control?
Oh, yes. P options. Pick it up, control. Okay.
Okay. Perhaps it's my connection. Okay. Give me just a minute to pull it back up. I'm sorry.
No problem.
Give me just a minute. I'm pulling it up again. Give me just a couple more minutes. Can you guys see my screen?
Yes,
Okay, Victor, if it's okay with you, I prefer to run the slides on my end just to prevent any issues.
absolutely. Yes, no problem.
Okay, all right.
All right, thank you. Well, yes, as I was mentioning, this multi-well assessment of the fracture porosity can help us have a better understanding on the flow nature within the Floridan aquifer system and its confining units. For this investigation, we will be using the course of 4 ASR exploratory wells, which were recovered and delivered by the South Florida Water Management District. And also we're using oriented optical borehole imagery, which was recovered by the USGS. So if you hear me saying OBI, that's the acronym for the oriented borehole imagery, which is basically a continuous image of the borehole, which is also oriented with the help of a magnetometer that is working inside of that OBI probe. This here you can see on the left. This is our carbonate rock lab, where we have been processing, analyzing, and photographing the core provided by the district. And on the right, you can see this. We use this camera setup with an overhead rail to take multiple pictures of each core box, and then we produce a composite image to create a higher resolution image, so we can have that. So we can see great detail on the imagery. Next, please. And like I mentioned in the beginning, we analyze the OBI logs and complement our findings with the core samples to do our fracture classification, which will be discussed in the next few slides. This on the left, we can see it's how a fracture will look on this is an unfolded picture of a 360-degree image, which is the borehole image. And the picture in the middle is a 3D interpretation of that same unfolded image. Basically, it's a virtual core section. And on these images, we usually look for references such as the brown bedding we can see on the top of the sinusoid. Just for example, either on the center or the left image, on the very top, there's a brown bedding. And we use these references as a reference to make sure we're looking at the same thing on the core sample. And we can see on the top of the fracture, you see, for example, in the middle, we can see that that red plane, that red dipping plane. It's just, you see the brown strata, and it's about 1 feet, a little bit over a feet over that fracture that we marked. And on the right, we see the core box. These are 2 feet of core. The core boxes are about 2 feet long. So we can see the red circle where we can corroborate that we're looking at the same section. So the main 2 aspects that we're looking for in this study are the orientation of those fractures and the relationship to the aquifer flow zones. Next, please. Here we can see this is a flow meter, the flow meter data for the first site that was completed, L63N, where we can see how the low flow on the top is marked with the red arrows, the low flow on the top, and the high flow spike in the where exactly in the same zone where we see the fracturing. So as this study progresses, we will be able to know more about how these fractures, preferential orientations correlate to the flow patterns and distribution. Next, please. And this is pretty brief. Just for our quality control, we're keeping an eye on the on those markers that like that brown rock that we discussed, with the core and the OBI to check for depth consistency. That's just to make sure that we're keeping a log of these depth checks every time we have an opportunity. We see a reference point. The core box on the left, it's outlined with a yellow color. It shows some interclasts. We can see some interclasts in the where the red lines are. And on the right, we have the OBI log, and we can see where we can correlate that same transition of rock. And right on the OBI log, we see a much clearer, lighter color rock. And right on top, we have those interclasts, and we see the exact same thing on the core box, and we keep our log. So in this case, we found that there's about like a 1 inch to 2 inch difference between the core box and the OBI log. Next, please. Now, moving on to the approach that is very important for fracture analysis. This chart here is showing us Lucia's Vogel pore space classification, which has been the standard for carbonate reservoir modeling by oil companies since the 1980s. And the reason for that is because the concept of Vogel porosity takes into consideration the geological processes that altered the rock after this rock was formed. Processes such as fracturing or diagenesis. So the main two pore space subclasses for the boggy pore space concept are the separate Vogue pore spaces and the touching Vogue pore spaces. The separate Vogue pore spaces, we can see it's on the left, means that we can have large pore spaces like the molds on the example. You can see molded pores on the example on the top left. But these molds, their interconnection will be depending more on the interparticle spaces within the rock's matrix. So elevated porosities on the separate box don't necessarily translate to high permeabilities because those interconnections will be dependent on the rock's fabric, as the chart states it, right? Grain dominated fabric or mud dominated, it will all depend. And on the right on the table, we see how the fractures or dissolution can create a flow path across the rock's framework. Now, fluid moving through these touching blocks is much less affected by the rock matrix because fracturing or dissolution or brecciation are not necessarily related to the genesis of the rock. These are geologic processes that just dissolve or cut through the rock, creating these flow paths that are like greatly overlooked because it's difficult to analyze them solely on a rock sample. Next, please. And this chart is a little bit busy, but it's just, this is our modification to Lucia's pore space classification. We have the separate Vogues, we have the fracture pore space on the center that we see on the blue-green color. We have that fracture pore space, which is a subclass of the touching Vogt porosity, which we were discussing how the conductivity is much greater. But we're making a distinction between the natural fractures and the induced fractures, because structural data for induced fractures have no geological significance in our study. You know, these are fake fractures, if you want to call them that way. You know, that happen usually because of the drilling process. So next, please. This graphic is it's just a screenshot of the same fracture classification, which was made into a WellCat library. WellCat is the software that we're using to analyze the fracture data. And so having each fracture assigned to its corresponding pore type will be key for having accurate interpretations and models. You know, if we put together induced fractures with natural fractures, then our data is not going to be reliable. Next, please. To identify the fractures on the OBI log, we typically look for this sinusoid. It's a very thin line on the left on top of the OBI image. That's the sinuses that we're looking for to identify the fractures that were created by geologic processes. So natural fractures, which are normally created by natural systematic forces, will show like this on the OBI logs. And that's our like most basic guideline. But induced fractures, like I mentioned, which are created by drilling or coring or core handling, even though they are caused by in a much more abrupt manner, they can sometimes be confused with natural fractures. Next, please. And it's very important for us to be able to make a distinction between those two because of the factors that I just mentioned. And these are the general characteristics that we're looking for. Fractures that look rough, there's fresh breaks, there's plumes on the core axis, there's planes that are parallel or normal to the core axis. Anything that will suggest that fracture formed rapidly or during a single fracturing event. So if we find some of these indicators, then we proceed to assign the type of induced fracture, which are several different types of induced fractures. Next, please. And in this example, this is an interesting subset, a little bit zoomed out, but it shows a lot of the markers that we can interpret as an induced fractures. It suggests that these fractures might be caused by the drilling process. Now, these characteristics are specific for induced pedal fractures. That's the classification. It's a pedal fracture, which is one of the most common induced fractures. And we can see, obviously, on the 3D interpretation and the image on the right with all the fracture planes, we can see that obviously the pedal shapes closely spaced one to another. On the unfolded on the left, on the unfolded 360 image, we can see that they're nested. They are all originated kind of from the same spot. And like I said, it can look, if you are able to see some red lines that we put to mark those nested fractures, we can even see some vertical fractures in the nesting section. And they are very closely spaced. They are usually, the recovery is difficult. They might form only on one side. We can see also on the unfolded image, the positive part of the sinusoid is visible. So that, but not some of the negative ones, the ones that go down, they're not visible. So that means that we only have the fracture on a part of the core, which is odd because the fracture would have gone through the whole core section if it was a natural fracture. And another really big indicator are the rib surfaces. I apologize, this image might be a little bit too zoomed out, but it's just to show all those factors. In the center of the unfolded 360 image, I don't know if you can see there's some, they look like steps, which is that there's a fracture in the center, and we can see some stepping. This is called rib surfaces. What the rib surface is suggesting is that there was incremental downward growth, and like I mentioned, it's difficult to recover. But if we can see these markers either on the core section or the OBI log, then we can make an accurate distinction between these types of fractures. So that was pretty much our summary for the approach we're taking for the fracture analysis. Next, please. Finally, I know we might be a little bit short on time. So quickly, I'm gonna show some examples of how these data that will derive from our analysis can be used for subsequent studies. I'm gonna go a little bit quickly over them. Kevin, if you see that I am omitting something, please feel free to jump in on the last examples. Next, please. Okay.
5 minutes.
All right. So these graphics that we see on the center, on the left, and on the right are from a model on the Cretaceous carbonate sequences in Texas. And this model is analog to the depositional environments found in the Avon Park Formation of the Floridan. On the left, on the very left, we can see 3 different depositional environments for these carbonates, which are the subtidal deposits, the tidal flats, and on the top of the cycle, the evaporites, just like we can find them in the Avon Park. And in the picture on the center, we can observe how they show that evaporite zone at you see the pink strata, the pink limestone. On the very top, we have that, which would be the tidal flat deposits. On top of that, the cap would be the evaporites. And they show that it's a dissolved zone, which would create accommodation space for brecciation to occur on the units above. And we have seen many of these collapsed breccia structures on the OBI logs we have been recovering. So being able to correlate the lithophases with certain fracture types and fracture orientations, it can be very valuable information. Next, please. So in 2007, Emily Richardson used ultrasonic and also OBI logs, just such as the ones we're using, to create this fracture flow orientation model that we see on the slide. I believe the publication stayed in draft mode, but of course, next, please. Once our study is complete, we would be able to correlate these results from Richardson in 2007 and compare our data to the regional structural models, such as the one here by Pindell in 2020. And then we could have a better understanding of how the groundwater flow relates to regional tectonics. Next, please. We can already see there is a correlation. I mean, we can assume there's a correlation with the with Richardson's northeast, southwest, and northwest, southeast trends, which would fit with the Florida master fold and its antithetic and synthetic folds. Again, it would be really interesting to compare with when we have more data for these studies. Next, please. And to wrap it up real quickly, another thing that could be also verified and enhanced, it's that could verify and enhance our results would be comparing it with regional 3D seismic models, which there's one published by Cunningham in 2018, and I believe there's more work that is being done for these seismic models currently. Next, please. And again, well, this is the same graphic with the orientation of the major structural features, regional structural features on Florida. It was tilted to match the orientation of the seismic model. But we can already make some assumptions about how the regional orientation of those fractures can relate to this seismic model by Cunningham, and that would be it. I don't know if there's any questions.
Thank you, Victor.
Thank you.
So we're going to start our panel discussion session. Any questions for Victor?
Anna, I do not see any hands raised at this moment. Oh, wait. Dr. Renee Price just raised her hand. Do you want to go ahead and give your comment or question?
Sure. Victor, too, that was a really interesting talk. I have a question about the regional fracture patterns figure that you showed for the Upper Florida Aquifer. And it was overlaid on Lake Okeechobee, and I was wondering if there was an attempt to overlay the aquifer storage and recovery well locations on that map.
Yeah, if we can go back to the slide, it should be this one, right?
Yes.
Correct. So I'm sorry, what was the last part of the question? Apologies.
So the aquifer storage and recovery wells that have already been drilled and are planned for this project, are they shown on this map?
No, this I am not sure. Let me see. The recent ones are not shown in this map. This is from 2007.
Okay.
Yeah, no, but like I said, this study was stayed in draft mode for what I believe, and the orientation that are shown is for other locations, not for the L63N or any of them. The recent.
But it's specific. It's specific to the Upper Florida, not the APPZ.
Correct. Yes.
Okay. Thank you.
Thank you.
Okay, I don't see any other hands raised. We want to move on to the next presentation.
Yes, thank you, Liz. And our next speaker is Dr. John Leslie. John works as a research microbiologist at the U.S. Geological Survey in St. Petersburg, Florida. And John's presentation will be on the characterization of microbial and geochemical processes contributing to nutrient reduction and potential clogging. John, if you are ready, please take it away.
Right. Thank you, Anna. Today, I'm going to give you kind of a brief overview of the project structure for looking at microbial processes that might be contributing to bowel clogging and nutrient reduction. And we've decided to include or combine or connect the nutrient reduction idea, because it seems to get a lot of press, a lot of attention with the bile clogging processes, because really what the bacteria are doing when they do remove these nutrients, nitrogen, phosphorus, and carbon, as we'll talk about in a minute, that's really to either minimally maintain the energy for existence in the aquifer. And if there's enough energy there by their taking up the nutrients, then they increase their biomass, which leads to the bile clogging. So there's a natural connection there between these processes, and that's what this project is trying to characterize. Okay, next slide, please. Next slide.
Yeah, sorry, Dr. Lau.
That's all right.
It doesn't seem to be advancing. All kinds of technical issues today.
Oh,
okay, here we go.
Right. Now, this is kind of a cartoon project summary that I'm going to stay on for a second. Then I'll got some pictures of real lab images later on. And the way this is set up is first we're going to collect one core from this continuing core process. It's been already highlighted in a couple of talks. And we're going to collect one core per depth, 2 depths per well. And each core section that we collect from each depth is going to be split into 2 sections. And one section is kept complete and stored stored so it's able to maintain the native bacteria within the core. And what we do with that section of core is we place it in a gas-tight core storage tube that's been flushed with argon gas. And then once the core is placed in that tube, then there's a positive pressure of argon gas maintained. Then it's stored at 4 degrees centigrade, as you can see in that cartoon as it goes down the left side of the image. And then it's stored at 4 degrees until the experiment that uses a triaxial cell permeameter to determine the bile clogging rates using this natural piece of core material that's been stored. So the second section of the core that's collected, it'll be sent off and crushed and sieved to specific screen sizes. And then a selected set of sizes will be used to pack 2 columns. One column will be packed with crushed core material, just the way it comes back from the processor. You know, we're going to have to probably wash that and maintain it and clean it up a little bit. And then that'll be used to pack one of the columns. And the second column, which is kind of unique to this study, because when you look in the literature, most of the time, in fact, all of the time, is they'll take either sand or core material or some type of crushed material. They'll crush it, dry it, do all the geological things to it, and then they'll use it to pack the column. Well, we're going to take like a new perspective and add another type of column in there, where we'll take the same material that we packed the first column, except this time, instead of immediately connecting it to the surface water pump system, we're going to allow it to grow its own set of natural biofilms that's from the groundwater system at the Kissimmee River ASR site. So now we've got a one column that's using the crushed material that's run in more of a traditional style. Then we've got a second column that uses the same material, except this time it's got the native biofilms grown on it before we go through the method that I'll describe later. And I think that this is important because it actually gives us a more realistic picture or image or characterization of what's going on in the subsurface. And then a third type of column, as you'll see on the bottom there, is just glass beads. And these will be 2 millimeter diameter glass beads that have been washed and acid washed and prepped a little bit to take some of the charge off of them. And that's going to be used more or less as a control. Now, the surface water, as you can see in the lower center there, will be collected from streams or lakes, which will be eventually used as a source water at the ASR facilities as they're developed and built. And these volumes will be transported back to my lab in St. Petersburg. While we're collecting the water, The water will be run through a 300 micron pore size filter, similar to the rapid sand filters at the projected to be used at the ASR treatment facilities. The source water, once it's collected back in the lab, will be pumped to each of the columns using a peristaltic pump, and we're going to run those rates at about 2 mils per minute in an upflow direction in all of the columns, regardless of what the column matrix is. Biofilm development rates will be quantified using a flow cell and 2 millimeter diameter glass beads and evaluated under a microscope. And that's that far right image over there. And that's allows us to try to indirectly measure the biofilm development that's going on in the columns, because we're not going to be able to use a destructive mechanism to get to these same type of data. So we're running a kind of like a biofilm development rate study along with the crushed core columns. The pumping pattern or flow patterns that'll be used on each one of the experiments, regardless of which of the columns that we're using or the flow cell, is there'll be 1 to 2 weeks of water flowing through the column, and that's to mimic the recharge phase of an ASR system. After that 1 to 2 weeks of upflow of the source water, each column will be valved off on the inlet and the outlet to make a static condition within the column. And that is to mimic the storage phase of the ASR facility. Then after 3 or 4 weeks of static storage, then the valves will be opened again. The source water will be turned on and pumped back through. And this will take place for 1 or 2 days. And that'll mimic the recovery phase of the ASR system. Okay. Now these columns will not be run simultaneously. They'll be run in a specific sequence. And the first column they'll be run is the glass beads using the surface water. The next will be the crushed core with no native biofilms. And then the crushed core with the native biofilms. And finally will be the solid core with the triaxial cell permeameter. Okay, next slide, please. Okay, where are the cores going to come from? And we'll be collecting cores from 3 well sites. And currently it's that C38S is where we're working at currently. The second one is the L63S. That's over to the eastern side of Lake Okeechobee. And the third site has yet to be determined. There's discussions going on about that as we talk. Cores from each site will be collected from 2 zones within each well, one in the upper Floridan and one from the APPZ. And this kind of summarizes what I've already talked about. From each core, recovered cores will be used for a solid core segments for the permeameter, and then the crushed cores for the 2 packed columns, one with native biofilms, one without. Okay, next slide. Okay, the core collection, stabilization, and processing is, I'm showing you how we do this in the field. And this was at C38S. And as they pull the cores up from the zones that are of interest to us, to me, then they laid out do all their geologic recording that's required. Then at that point, I select out a section of core that'll be stored for eventual use with the permeameter. And what we do here is we take a continuous section of it and then go to the upper part of the diagram there. And you can see that I'm sliding that into a polypropylene sleeve that has holes drilled in it so that the gas, once it's inserted into the larger core tube, pressurized tube, that'll maintain the structural integrity of the core during storage. Okay, then once that is is completed, I drop that into the gray core there as you can see in the back of the vehicle. That's dropped into this container, this tube. It's sealed off, and the whole time we've got argon gas running from the top to the bottom to flush out the oxygen. This is all bolted down, made airtight, and then it's pressurized with excess argon gas to about 20 to 50 psi. Another section of the core then is taken taken to a commercial crushing and screening vendor. They do this for us. And then you can see there that that's kind of what it looks like when it comes back to us. And then that's used to pack one of the columns. Next slide, please. Now, these are images of the 3 types of columns, kind of in sequence, that how we'll go about processing these. And you can see the glass beads on the first one. The crushed core with no biofilm would be the middle image, and the crushed core with the native biofilms. And these are just staged because we haven't gotten to this point yet. Then what you see, these protrusions on the left of all the columns are the pressure sensors. These are Bluetooth continuous pressure recording sensors that download their data to computer programs that allow us to 24-hour-a-day pressure monitoring. The columns themselves are 3-inch in the inside diameter and 12 inches long. And they've, in the preliminary experiment, these have worked out quite well. Next slide, please. Okay, now how are we going to grow the biofilms on the crushed core columns for that third column that I described? And we take those columns and that I showed you, and we fill them with the core material. We take the sensors out and put plugs in those holes so that you know, we can't put the sensors in the groundwater because it's so aggressive. Then we place that into an above ground mesocosm that's been at the Kissimmee River ASR site at monitoring well 10. It's pulling water from the upper Florida. And it's been in place, gosh, I guess maybe a couple of years. And it's got a continuous flow of groundwater from that depth running through the through this box. And we're able to control, if you notice to the left of the box in the lower edge, you can see lots of black lines that lead into that. And those go into flow control valves. And we're able to take the high flow coming out of the well and reduce the rate down to where it's close to what goes on in the at depth, in the aquifer depth. So what I'm able to do here is then I'll connect these columns that are filled with the crushed core into this groundwater flow mesocosm and let them sit there as the water upflows through them and colonizes this virgin core material for a length of time. Preliminary work has shown that about a 2-month period is required for a healthy biofilm to develop and still be a representative of what's at depth. Next slide, please. Okay. Now, this is what the lab setup looks like. We had originally planned on doing this at the Kissimmee River ASR site, but there's been some logistic issues there that was going to make that rather difficult. So the project management team there at South Florida agreed to let me move this to my lab in St. Petersburg. And this is kind of the way it's set up. And you can see the surface water collection carboys are there to the left. And we've got about a capacity of about 100 liters. And the water flows out of that into a sensor flow cell. And what's connected to that flow cell is a set of sensors that will be set up to record the data, which I'll show you the data they'll be collecting in the next slide. But they'll be collecting that on probably like a 1-hour basis continually. The water flows out of that sensor cell into a bubble trap that's needed because of you don't want to exacerbate the gas bubble trap issues in the column by introducing bubbles from the water column, from the water source. The peristaltic pump then pumps that water into the columns from the bottom in an upflow manner. You can see the pressure loggers there, they're in place. That water flows out of that, then flows into a second sensor cell, which will be recording the same parameters. So we've got an inflow or prior column, after column set of field parameters. And then after that, it flows into a, excuse me, a sample collection bottle, and from that's where we'll collect some of the samples for the nutrient and metal analysis. Next slide, please. Now, these are the types of the data variables or variables we'll be collecting data on. From the carboys themselves, we'll be, prior to even starting the experiment, we'll be collecting samples for nutrients. That's carbon, nitrogen, phosphorus, cations, anions, and redox sensitive metals. And the first sensor, the sensor meter, the YSI meter, it'll be measuring temperature, specific conductance, conductivity, TDS, salinity, DO, pH, and ORP. The pressure sensors you see there in the column, they'll be collecting pressure too. They'll be set at a certain data collection rate. The second sensor, flow cell, will be collecting the same data as the first one. And then the sample, the data collected from the sample will be the same as that collected for the incoming water, or the source water. So you can see what we've got here is a way of looking at the water quality before it goes into the column and after it comes out of the column. And this is like after the storage period, per se, that I described earlier. Next slide, please. Okay, now what kind of nutrient geochemical analyses will be conducted on these samples that I showed you before and after the columns? And the carbon samples will be analyzed by Dr. John Kominowski at Florida International. And he'll be doing the DOC, TOC, and the SUV 254s, which shows the aromaticity of the organic carbon before and after it goes through the column. Then it'll also be analyzing the DOC from these BDOC columns that I've set up. I don't know if you're familiar with BDOC in the drinking water industry, but this technique or method allows you to get a better idea of like what component of the DOC or TOC in this case is available for biological activity, which are biologically active, something that the microbes in the column will be able to utilize, and which again is important because we're looking here at nutrient mineralization, and carbon's a major player there, of course. And so what we do here is, that drinking water method, which is in standard methods, is what they'll do is they'll take a set of sand from one of their rapid sand filters, a known mass of that sand, and they'll put it into a flask of water coming from their source, like from a river per se. And then they'll look at the DOC in the water before they add the sand. And then after like a week or two of having the sand interact with that source water. And what that tells them is that their filters, like what component of the water coming into their treatment plant is biologically active or removed by their filter system. So it's a biological remover, not the physical removal. So what I've adapted this method or this concept for our column studies. And what I'll end up doing there is I'll take that same crushed material, put it in a smaller column, and then connect that into the above ground mesocosm that I just described for the larger pack column, and allow it to grow a native groundwater biofilm. And then I'll take some of the water from the source water, from those larger carboys. And then once this substrate here in these smaller columns has the natural biofilms grown on it, then I'll use that as what they call the seed, the biological seed, and then look at the DOC, reductions in DOC from time zero over a certain amount of incubation. And that gives us an idea of how much of the carbon that's going down the well is actually immediately available for microbiological mineralization and biomass production, again, contributing to that biomass or bioclogging component. Then the nitrogen and phosphorus species will be analyzed by Rob Masserini at the University of Tampa. I've used him before in that last nutrient removal study. He's got a very high-end nutrient analysis system that's a research grade. He does great work. Glad to work with him again. And the geochemical analyses for the cations, anions, and redox sensitive metals will be done by Eurofins Test America. Next slide, please.
5 minutes.
Okay, project update. As of today, we've had one core removed and retrieved from the first site at C38S. That solid core has been stabilized and in storage at the St. Pete lab. The core section for crushing is currently being processed, and we're waiting for that to come back. And once we get that, we'll be able to start all of these experiments I've just described for you that use crush material. To date, all laboratory systems that are required in the statement of work for this task have been set up. Trial experiments, optimization studies have been done to make sure everything's working real well. And what I want to finish up with, kind of give you an idea of something I have been doing that I thought you might be interested in, is this biofilm development assay that's used by, that's characterized by looking at it under the microscope. Next slide, please. And here you've got the setup that I used. And on the left, it's Kissimmee River water that's 300 micron filtered that I collected on one of my trips down there to kind of look at the place. We've got to pump that through, or pull that through a bubble trap. It goes through the peristaltic pump. And again, kind of as with the columns, it goes through this biofilm flow cell. And the flow cell is filled with 2 millimeter glass beads, similar to the control column I described earlier. Using the same flow rates we're expecting to use in the larger columns. And I did this pumped the water through this flow cell for about a day. And then at that point, I valved the inflow and outflow out, covered in black plastic, and left it sitting as is for about 2 weeks. After 2 weeks, I take it off the clamp, remove it from the pump system, and take it to the microscope. And you can see on the right-hand side how it fits into the microscope stage, stabilizes it, and allows me to get images of the beads, and in between the beads, as you'll see here in a second, with the microscope, and take images as well. Next slide, please. Okay, so here's what we looked at. Now on the left-hand side, you've got 2 images of different zones in the flow cell. And you can see this is what the glass beads looked like at time 0, naked as I call it. No water's been Kissimmee River water has touched them yet. Okay, pretty clean, pristine. After the 14 days under a visible light microscope, this is what it looks like. And I tried to capture the same zones I looked at originally there on the left. And you can see that in between the pores and in between the beads, you can see the development of encatchment of material that was in the source water being pumped through the flow cell. And also the growth of some biological component. Also, the brownish tint you see there is not the microscope issue. That is actually some of the color is associated with the groundwater that makes it through that 300 micron pore size filter that attaches to the glass beads and coats them quite well. The third greenish looking slides, this is a DNA specific stain that I've used quite a bit looking at staining for bacteria and viruses in all types of water systems. And if you look real close on the surfaces of these beads, you can see really bright green spots. Each one of those spots, or length spots, represents either an individual bacterial colony or cell or a colony. And due to the magnification issues, I can't really get down to 100x. You have to wait you kind of got to go by like the brightness represents a bacterial colony, but you can see that there's colonization of these glass beads, and within the same zones that you see in the middle set of slides. Now that last image that's purple and kind of looks like the moon, that is after I stained this entire flow cell with crystal violet. And this is that biofilm development system or characterization system I want to use. And anything that turns purple is a biofilm. Now the thin purple represents, it could be proteinaceous material, it could be carbonaceous material from the water, but the dark pink or dark purple zones, those are bacterial colonies of biofilm development. So you can see that even after 14 days on glass beads, that the water that from the Kissimmee River can not only colonize these glass beads, but actually form colonies in small biofilms on the surfaces and probably in between the pores that between the glass beads. And with that, I think I'm done.
Thank you, John. Are there any questions for John?
I currently do not see any hands raised from our panel members.
Okay.
Should we wait another couple minutes, seconds?
Okay, or we can move on to the wider panel discussion. And if there are questions for okay, so if there are no questions for John, we're going to move on to our public comment session. And please remember to raise your hand, and Liz will call your name in the order the hands were raised.
Okay, our first up is David Pine. Please state your comment. David, we cannot hear you. You may be muted. Do you want to try again? Okay, we're not hearing anything from David Pine, so we'll try to come back to him. Let's move on to our next public commenter, Paul Julian.
Hi, this is Paul Julian, audio check.
We can hear you.
Cool, excellent. Thank you. Paul Julian, SCCF and Conservancy of Southwest Florida. Thanks for having this workshop and having all this wonderful information given to us. I put in a couple questions regarding Dr. McDonald's presentation and the Q&A function there. It's just kind of out there. And I don't know if it's, if you want me to reiterate it, I can.
Actually, today we were just accepting public comment, but we will reply to your Q&A questions.
Okay, cool. Well, I guess, yeah, I mean, ultimately it's good that we're digging into the science of ASR, the ability to understand things that are going on below surface is pretty important, especially the key topics there. And just keep up the good work. Thank you very much.
Thank you, Paul. At this time, I do not see any other hands raised. I think we should probably give it a few seconds. Oh, David Pine has his hand raised. David, do you want to go ahead and state your comment? It looks like you're muted right now. I'll tell you when you're unmuted and maybe you can start trying to speak. It looks like you're muted. Okay, we're going to go on to the next public commenter.
You're muted. Hey, Liz, does somebody need to unmute David?
Yes, but our IT is online, and so they were unable, they were able to unmute Paul Julian, so I know that it's working. So there must be something wrong on David Pine's end. Let's move on to the next public commenter, Christian Prieto. Christian, do you want to state your comment?
Yes. Can you hear me?
Yes, I can.
I was hoping you could elaborate on the significance of the biofilm to the aquifer, or in the wells that they'll be applied to.
We actually are not accepting questions at this time. We're looking for more public comments. There will be an opportunity for the public to submit comments and questions on the ASR science plan once it's posted, but this is more for public comment.
I see.
Okay, anyone else from the public have a comment? If so, please use the hand raised feature. Okay, our next speaker is Jake Fojic.
Yeah, good morning. Thank you. This is Jake Foytik with the Florida Farm Bureau Federation. I just wanted to reach out and say thanks for all the hard work that y'all are putting into this. I know it's a lot, and we appreciate it. At the Farm Bureau, we have policy supporting alternative water storage and alternative water supply, and we just see this as a great opportunity, and we appreciate the openness of this whole process. So thank you.
Thank you for your comment. Any other public comments? All right, next up is Ernie Barnett. Go ahead, Ernie. It looks like you're muted currently. Please unmute yourself.
Hopefully you can hear me now.
Yep.
This is,
Yep,
Ernie
I can hear you now. Go ahead.
Thank you. Echo the comments of an excellent workshop so far, and I'm excited to see the great progress that's being done in the science. The one question, or not question, but just kind of observation I'd like to make is that I think there continues to be a sort of a lack of understanding by the general public, not by the folks on this panel, that there is a very protective regulatory program that will make sure that a lot of the questions are answered through the science plan, but also through the regulatory criteria that is placed on all of the permits. And DEP, worked at DEP for over 22 years and can attest to the protective nature of the UIC program. And with that as a backdrop, the main comment I'd like to make is I think that as the wells come online, that there should not be a delay in the cycle testing. I think the more expeditious we are in implementing the ASR cycle testing, we can learn as we go and demonstrate that there are operational protocols that can be extremely protective for issues like arsenic, the bacteria, viruses, protozoan, nitrogen, phosphorus, and the like. And that without that data that we would collect from the geochemical and water quality data collected from the ASR cycle testing, it could delay significantly the implementation time. So the main point of my comment is that once the wells are done, I think we need to, even if there's some sort of partial treatment put in place, expedite the implementation of the cycle testing so we can have the additional data and information we need to demonstrate that this will be a very safe and important technology that will be critical to the long-term restoration of the Everglades and the management of Lake Okeechobee. Thank you.
Thank you. Any other comments from the public? All right, I do not see any other hands raised. So Anna, I'll pass it back to you.
Thank you, Liz. Can we move on to the next slide, please? Okay, and now we will take a lunch break and we will restart the workshop at 12:30 p.m. sharp. Thank you very much and see you at 12:30. Welcome back, everyone. Before we get back to our presentations, I will quickly go over the remaining workshop schedule. We will have 6 more presentations this afternoon with a short 15-minute break at 2 p.m. Also, we will have a 30-minute panel discussion session around 3 p.m. And during this session, our panel members will be able to ask questions, and our presenters and team members will be happy to provide responses to those questions. We're also going to have a public comment session at around 3:30 p.m. Just as a reminder, during this session, we'll only be taking comments from the public on the progress of the work presented here today. However, the public will be given a 30-day opportunity to submit questions on the projects related to the ASR Science Plan during the 2022 ASR Science Plan review, which will take place later this year. And we will send a public announcement about that public review when the time comes. And now let's go back to our presenters and our presentations. We'll move on to our next speaker, Heath Vince. Heath works as a professional engineer at Stantec, and today he will give an update on the treatment technology proof of concept testing. And with that, I will turn it over to Heath.
Great. Good morning. Thank you, Anna. Yes, we'll be going over an update of the proof of concept testing, treatment technologies. My name is Heath Wentz. I'm a professional engineer at Stantec. Do you want to go to the next slide? Great. So the intent of proof of concept testing was to identify and summarize performance characteristics of both media filtration of the water and UV disinfection, along with membrane filtration to evaluate backwash solids, characterize those, and conduct a non-economic evaluation of these treatment technologies to determine what kind of performance we could expect for treated water for storage. We'll go over the foreseeable schedule and next steps. Next slide. So proof of concept testing was intended to demonstrate and test treatment systems that can produce water that is suitable for aquifer recharge per Florida Administrative Code, including coliform bacteria removal down to 4 CFU, which is colony forming units per 100 milliliters, and to assess the potential for removal of color and dissolved organic carbon that is prevalent in the Kissimmee River. Next slide. Proof of concept testing was also conducted to test up to 2 different coagulants and to test membrane filtration with those coagulants, consisting of 2 ceramic membranes and 2 polymeric membranes. We'll go over those later. We also wanted to test dual media filtration as a pre-treatment to UV disinfection, similar as to what is currently what was previously constructed and operated at the Kissimmee River ASR facility, and to evaluate the ability of pressurized UV reactor technology to meet disinfection criteria. We also wanted to characterize the backwash waste from our pilot operations for dewaterability analyses. Next slide, please. So this is the existing Kissimmee River ASR facility. And what you see in the black lines are the facilities that were temporarily constructed for this testing. The green line that you see starting in the bottom right, the existing raw water pump was used. And as the color coding of lines, green is raw water. That was sent to a strainer and bypassed the existing filter. And then it was routed around to the first membrane treatment system and the media filtration and UV treatment train, and then the next 3 membrane treatment systems. So there was a constant supply of raw water that was being circulated in excess of what we needed and routed back to the river. So it was just raw water recirculated back to the river. Treated water from these processes was then routed either to the pond to the north or back to the discharge cascade aerator structure. Next slide, please. So just a quick performance summary of what we found. Membranes, both microfiltration and ultrafiltration, removed coliform bacteria by size exclusion. The size of the pore size of the membrane is about 5 to 50 times smaller than a coliform bacteria can fit through. And we found that membranes removed significant amounts of color with the aid of a coagulant. Ceramic membranes, we found, used a greater amount of coagulant than polymeric membranes and would correspondingly produce a greater volume of solids for management in their backwash. However, ceramic membranes demonstrated the ability to reduce color by 93 to 95%, which is down to 7 to 5.5 PCU. That's platinum cobalt units it's measured in. And ceramic membranes would meet the secondary drinking water standards for color for Florida Administrative Code, which is 15 PCU. So that 7.5 is almost half what the secondary standard would be. Next slide, please. So polymeric membranes, conversely, and we can see a few examples of these in the cross section that we see on the right. It's almost like hollow fibers, like spaghetti strands with a hollow core in them. We found that polymeric membranes reduced color by around 50% to approximately 50 PCUs, which would not meet the secondary standard, secondary drinking water standard for color. What we found from media filtration and UV disinfection was that media filtration prior to UV helped with solids and turbidity reduction, but was unable to reduce color or dissolved organics to meet the secondary drinking water standards. And so that treatment technology would require a water quality criteria exemption from DEP. The UV treatment system evaluated under Alternative 1AB does not rely on chemicals for disinfection. However, the high color of the surface water makes it kind of tea colored, and the correspondingly low UVT or UV transmittance, we call that, how easily the light penetrates the water to disinfect and kill those bacteria. That lower UVT requires significant doses of UV light to remove coliform bacteria. Next slide, please. So we found that media filters did not remove coagulated DOC or dissolved organic carbon. The particle sizes were 10 to 100 times smaller than that which could be captured by the sand media in the filter. So as you see on the figure here, to the right, you see a sample of coagulated water. And with conventional media filtration, that green box on the graphic, that's the size. The red arrow points to the size at which it might be able to effectively remove particles. But toward the left, and the x-axis in this graphic is particle size in microns. we're looking at almost 2 orders of magnitude smaller particle sizes that we are trying to remove from this process. So if the media filter, the sand in the media filter was unable to capture that, we saw aluminum from the coagulant, almost 80% of it was passed right through this filtration process. And this represents what would be passed downstream for storage. Next slide, please. So the takeaways from media filtration and UV were that media filtration would not remove DOC and would require a water quality criteria exemption. The low filtration rate for media filters translates to a large facility footprint. Backwash ponds for sand media filters would require significant land. Even at low filtration rates, media filters minimally reduce turbidity in solids, resulting in a high UV dose requirement. So UV can reliably disinfect water, but requires up to a 30 millijoule dose during poor water quality events, as opposed to a 21 millijoule dose provided at Kissimmee River ASR facility previously. So clean water source for backwashing is recommended, but might not be available from Okeechobee Utility Authority. Next slide, please. So for ceramic membranes, we evaluated 4 of them, nanostone and aqua aerobic. After a little bit of a shaky start, nanostone's nominal flow rate we found was not sustainable throughout all of trial number 4. Aqua Aerobic, the other ceramic membrane manufacturer, had very sustainable operations throughout the proof of concept testing, including trial 4. Next slide, please. Polymeric membranes, FilmTech and Suez. FilmTech had demonstrated a very sustainable operation during trial run number 4 once all the chemicals were optimized. Suez, however, we found had a persistently high coliform and their effluent throughout trial number 4. Despite many attempts to chlorinate the sample tap and membrane housing piping, unfortunately, we were unable to resolve that. So operations were otherwise very steady. Next slide, please. So this is kind of a picture's worth 1,000 words here. In our water quality summary, alternative 1AB, as you see toward the top, that's the media filter and UV performance. And alternative 2A, the different membranes, are what you see further to the right. So what we're looking at here are 5 different analytes: color, dissolved organic carbon, phosphorus, and nitrogen, and aluminum. And what we're looking at here is the percentage of reduction of each of those. So how well does this technology work at capturing the stuff that we want to take out of the water before storing it? And you can see media filtration and UV did not remove color, DOC, or any of these parameters very effectively. We did see that FilmTech had polymeric membranes, FilmTech and Suez had slightly better performance for capture of phosphorus and nitrogen, but color and dissolved organic carbon still both remained fairly high. Conversely, nanostone and aqua aerobic, the ceramic membrane technologies, removed upwards of 90% of color and up around 60% of dissolved organic carbon, removed almost 93% of phosphorus and around 50% of nitrogen. So green results here indicate favorable treatment, red results less favorable treatment. And these line up correspondingly to the columns above. Next slide, please. So primary drinking water standards were met for all treatment trains except for Suez during the extended trial number 4. Secondary standards were met by ceramic membrane manufacturers, including aqua aerobic and nanostone. Next slide, please. So laboratory analyses of these treated water, treated water, quantified the solids that were remaining in the treated effluent of each treatment process. So we derived from that the maximum dry solids production from each treatment train, which is the sum of dissolved organic carbon removed, total suspended solids removed, and coagulant added. So higher doses of coagulant yielded greater amount of solids in the backwash process. So you can see that down below. Green results indicate lower numbers, and red results indicate higher numbers. So you can see nanostone and aqua aerobic, the red and orange numbers, are higher than the other ones. So they were more effectively removing these constituents from our raw water. Next slide, please. So what does that mean for aquifer recharge? So the converse of that is whatever is not captured in the filter backwash is what would be passed downstream for recharge water in the aquifer. Water from proof of concept testing was not used to recharge the aquifer during testing, just to be completely clear. However, the difference between the solids in the raw water and the solids in the backwash stream gives us an arithmetic difference, which represents the solids in the recharge water. So higher solids in recharge water to the aquifer indicates a higher potential for fouling, or more frequent need for acid, for maintenance acidization of the wells. So you can see that media filtration and UV had a much higher number here. So greater number of solids would potentially be passed downstream than polymeric membranes, which are in yellow, as compared to the ceramic membranes, whose results are shown in green. Next slide, please. So the backwash process. So every filter has to backwash to remove dirt and allow it to be put back in process and continue removing stuff. So membrane solids backwash content was, and then the backwash settleability, the ability of that backwash soup to settle out was highly variable. We found that the polymeric membrane backwash did not settle, and that additional coagulant we then determined we would try to use and dose on that backwash water to thicken the solids based on jar testing that we did in the laboratory in conjunction with the recommendations of the membrane manufacturers. So and as we're looking at this on this graphic, on the right, we're looking at the polymeric membrane backwash from Suez after 90 minutes. It looks fairly turbid, kind of, milk, kind of chocolate milky. And on the left, we're looking at the backwash from a ceramic membrane manufacturer. This is aqua aerobic, and you can see from the surface of the water that's reflecting light down to the settled solids layer at the bottom, it settles out pretty readily. So those thickened solids were then collected and sent to an offsite laboratory for a dewaterability analysis. Next slide, please. So those thickened backwash samples were sent to Andrit's laboratory for a centrifuge dewatering evaluation with 3 objectives: to analyze the physical properties of the sludge samples received, to conduct a polymer evaluation with the sludge samples received, and to conduct centrifuge spin down testing of those samples. So as they were received from us, there was a significant difference in the total solids content of each one of those. And the total solids were equal to the suspended solids for each one of these. What we're really looking for here, what we're hoping for in the backwash process, is around a 2% solids concentration for centrifuge dewatering. So as you can see, this would be challenging for both the polymeric membrane manufacturers, DuPont and Suez, since they're much lower than 2. Aqua Aerobic and Nanostone, the ceramic membrane manufacturers, those were almost 1.4 and 0.45. So those are getting to that target concentration and easier to treat to that level. Next slide, please. So, conclusions from membrane filtration. Coliform bacteria was reliably removed without additional disinfection technology. Excellent removal of solids and turbidity resulted in greater solids content of the backwash. We found that operations of membranes are very sensitive to coagulant dose, and that the parameters for operation and for design and operation vary significantly by vendor. Membrane life, chemical usage, settleability, and dewaterability of their backwash waste varied significantly. Next slide, please. Okay, non-economic evaluation. So how did these different treatment technologies compare? Next slide. So, taking into account the performance criteria of each membrane manufacturer, we developed design criteria for the remainder of the treatment facilities which would need to be constructed to operate each membrane or granular media filtration and UV. You can see all of them would require raw water pumping, hydroburst cleaning of intake screens, strainers, and then the design criteria differs a little bit in the middle between UV disinfection, membrane, so on and so forth. Some would require a flocculation sedimentation basin to further concentrate solids from that 1/4% to get it up to that 2% level for dewatering. And we also noticed the laid out design criteria for different chemicals that they would require for backwashing and maintenance cleaning. Next slide, please. And before we go on, the sum total of the area required for each one of these is then totalized as the process area subtotal, and then the overall site total, which is then converted into acres. So we get an idea across the board here what kind of land requirement each treatment alternative would have. Red alternatives depicting larger land footprints, green depicting smaller. Next slide, please.
5 minutes.
Thank you. We also looked at non-economic weighting of categories based on previous studies between color and organics removal, waste disposal, operational considerations, staffing requirements, minimizing risk for plugging the aquifer, reliability, constructability, and using previously established criteria, we updated the scoring of these. The considerations and operational considerations and reliability carried the greatest weighting of these various categories that we workshopped with district staff previously. Next slide, please. Okay, recovered water considerations. Next slide, please. So during previous cycle testing at the Kissimmee River ASR facility, arsenic was present in the recovered water. Arsenic during cycle test 1 was nearly 7 times the MCL, or maximum contaminant level. However, based on the data from the 2013 SRP report, this situation appeared to be a short-term commissioning type of challenge rather than a long-term or chronic problem. So the characteristics of proof of concept testing, treated water from each of our processes, conductivity, oxidation reduction potential, are similar to that of Kissimmee River surface water, and similar to that water previously used for Kissimmee River ASR testing. Next slide, please. So during the previous ASR testing, a first flush of recovered water was directed to a retention pond. For full-scale facilities, however, allocating large areas of land for retention ponds to address a short-term issue did not appear to be productive. So a regulatory approach to address arsenic in recovered water could involve establishing a mixing zone and could be discussed further with FDEP. However, if there is a desire to treat and remove arsenic during this initial cycle testing, membranes could be used to accomplish this with interconnecting piping and with bleach and oxidizer. Recovered water could be oxidized to convert arsenite to arsenate and precipitated out as a solid, which would then be coagulated and removed using either micro or ultrafiltration membranes. So membranes could have a dual purpose function or dual benefit if utilized. Next slide, please. So forward-looking schedule, I think I'm down to about 50 seconds here. We are in the process of finalizing our proof of concept testing report and taking comments back from district staff. And we are preparing a conceptual discipline design for a treatment alternative to conduct MCASES, evaluate an MCASES cost estimate for evaluation by core and district staff. And those should be wrapped up towards the middle of July and finalizing the testing report at the end of July in preparation for the TRB at the end of August. Next slide, please. So our next steps. Our next steps would be to develop conceptual design drawings based on an apparent preferred technology, to develop an MCASES detailed cost estimate for the core and district, to finalize proof of concept testing and the report and the TRB, and then go through treatment technology procurement and pre-selection so that facility pre-design could be conducted, survey, geotech, investigation, and the consultant could design an overall facility around one pre-selected technology. So next slide, please. Technology procurement would be a long lead time item, could require up to 12 to 14 months. And so it's important that this pre-selection step take place early so that the equipment is available on site as the rest of the facilities are constructed. Next slide, please. And I think I went a little bit over, but we'll turn it back to the panel then. Thank you, Anna.
Thank you, Heath. And now we'll begin a short panel discussion session. Any questions for Heath from our panel members?
Hi, Anna. Dr. Tom Messmer's hand is raised.
A question I have is, can you hear me first?
Yes, we can.
Okay. Did you add a coagulant before the media filtration, and if so, what was the composition?
Yes. So we tested ACH, aluminum chlorohydrate, and we tested doses at 5, 10, and 20 milligrams per liter. And we found that even the lowest dose of ACH, we were seeing that in the effluent in elevated levels. And media filtration it's kind of sensitive to the filter loading and how much volume you're putting through per square foot. And we tried to take this all the way down from 4 gallons per minute per square foot down to 2 gallons per minute per square foot. And we still continued to see coagulant passing through the filter and post-floc forming. Almost 80% of it, as indicated there. Does that answer your question?
Yes.
Okay, great, thank you.
I see Dr. Renee Price's hand is raised. Go ahead.
Sure. So I have a question about testing the recovery water, particularly during cycle testing. and you're appropriate that arsenic is a concern, but there's also some other concerns as well. I think we recommended testing for radionuclides, mercury, et cetera. So my question is, when will you design a sampling scheme to test for these parameters, specifically during cycle testing? When will we see something like that?
That is something that could only be done full scale. So in order to test the recovered water from the well for these radionuclides and different parameters that you're speaking of, that's something we can't really just take water from the ground from a well and sample. It would need to be water that was treated and then stored underground to be representative of recovered water. If that,
yeah, I understand that. So that it's going to be recovered, right? And so what is your plan for sampling and analysis and maybe storing that water until you get that analysis back?
I would need to defer to our hydrogeology team on that one.
Okay, thank you.
Hey, Renee, this is Bob Verastro. I think really what you're speaking of is ultimately going to be the cycle testing plan that we're going to need to develop when the first few wells get put into operation. You know, we're gonna need to really try to understand what these chemical processes are, but we're not going to get there until we put the first few wells into operation.
Oh, okay.
Very good questions. Thank you, Tom. Thank you, Renee.
All right, I do not see any other hands raised.
Okay, thank you, Liz. So we're going to move on to our next presenter, Joe Allen. Joe works as a senior wildlife biologist and risk assessor at the Formation Environmental, and he will give an update on the quantitative ecological risk assessment. Joe, whenever you're ready, please take it away.
All right, thanks, Anna. Can everyone hear me?
Yes.
Okay, great. Hi, yeah, as Anna mentioned, I'm Joe Allen. I'm with Formation Environmental. I'm a wildlife biologist and risk assessor. Formation is subcontracted to the Water Management District under Intertech PSI, who is one of the contract holders for the ecological risk assessment contract for the district. In this project, where the district has asked us to take a look at updating the quantitative ecological risk assessment process, and we're in the work plan development process right now. And talk a little bit about the history and where we're going with this thing. So next slide, please. Okay, so we're fortunate here in that we're not starting the ecological risk assessment for these ASR wells from scratch. We have a good baseline of data from the original ASR regional study that was completed back in 2015. There was an assessment of risk to the ecological receptors from discharge from those couple of pilot facility wells, both the Kissimmee River ASR and the Hillsborough ASR back in 2015. So we have that data as a baseline to move forward. Have next slide, please. Okay, just very briefly, what that risk assessment did was it took a look at a whole wide range of potential risks to the environment from release of the water that had been stored underground in these ASR facilities. It looked at everything from localized toxicity of the released water to bioconcentration. There was some extensive modeling done to see, you know, how those water quality changes might propagate downstream. And overall, it concluded that there was a low likelihood of risk to the ecology in Lake Okeechobee and in the Everglades from the operation of these ASR wells. A little more specifically, it identified that the highest risk was probably a physical risk due to impingement and entrainment of larval fish at the intake mechanisms. It concluded that there was a low risk of mercury methylation after the waters were put back into the surface water. There was some toxicity observed in the water samples that after the discharge, but it was fairly limited. And there was also some bioconcentration of heavy metals observed, but again, it was fairly minimal. The overall conclusion, again, that the risks were probably low and that the ASR system should be constructed somewhere in a large body of water where sufficient dilution can occur on release back into the ecosystem. Next slide, please. That report was reviewed by the National Research Council and by the members of this PRP. They did have a number of comments on the risk assessment, and what's on this slide here is kind of general comments of what needs to be improved with the risk assessment. And first, they asked us to take a look at longer storage times for the water, larger recovery volumes, some additional toxicity testing with some adjustments to water quality parameters, look and see what might happen in the ecosystem with changes in water hardness. They requested some additional bioaccumulation studies of in situ animals, so animals that are actually collected from the receiving water. And then they also requested that the risk assessment be more quantitative in nature and include some probabilistic risk analyses. So we're taking the data from the 2015 risk assessment. We're looking to expand and improve that, and we're going to use these comments and suggestions to help do that. So go to the next slide, please. So the district asked Formation to help out with this process. And the first piece of work product we put together was a scoping memorandum that we completed back in June of last year. And what the scoping memorandum was intended to do was just outline a way that we can get from the old data, the old risk assessment data, and incorporate those comments to update and improve the risk assessment. And the first piece that the scoping memo included was a recommendation to develop a risk assessment working group. And that working group has been developed. We started that up back in about mid-year last year. It's a working group that's led by the district and the contractors, the risk assessment contractors. And it includes, you can see the list of folks, organizations that have folks that are included in this working group. And the reason we did that, and the goal for this thing, because we recognize there's a lot of different ways you can do risk assessment. And this is kind of a big multi-armed project here. So we want to make sure that we're responsive to the stakeholders who are going to be interested in the results of this thing and get them included in the planning process so that we can put together a risk assessment that's as efficient and as cost effective as we can possibly make, while being technically defensible and answer the questions that need to be answered as we move forward in this process. And one of the key factors is, again, to utilize those comments we got from the NRC and the PRP group. Overall, the goal of the working group right now is to develop a comprehensive and quantitative risk assessment work plan. So if I can have the next slide, please. How we're going to build that work plan, this is just a very simple cartoon thing here, is that we're going to start from what we have available, and we've got a really nice baseline data set of water quality data, toxicity testing, bioconcentration testing, modeling, et cetera. We're going to update that data, and we're going to do it using some US EPA ecological risk assessment guidance. We have kind of a unique situation here is most risk assessments are based almost entirely on chemical toxicity effects. And we're going to take a look at that here, but we also have some physical stressors. As I mentioned, one of the conclusions of the original risk assessment was that impingement and entrainment were extremely important, or one of the most potential for the highest level of risk. So we need to take a look at that too. So there's some modifications to the risk assessment guidance that we're going to use. Have the next slide, please. So last year, due to some contractual issues, we weren't able to get really started on the work plan. So we wanted to use the time we had available to address some of the concerns with the original risk assessment. And as I mentioned, one of the concerns was that it was asked to be more quantitative. And since it is such a good source of data, we went back and we took a look at what we had available and tried to come up with ways that we could apply that original data to the planning of the new and updated risk assessment. And this document you see on the screen here was completed in December of last year, and it's a quantitative analysis of the bioconcentration and toxicity data from that original risk assessment. The bioconcentration data, there's an extensive database in there of both invertebrates, mussels, and fish tissue that were both collected from a lab setting and in situ in the Kissimmee River. But what the original risk assessment did was it looked at a simple numerical bioconcentration model. Were concentrations different downstream of the discharge point versus upstream of the discharge point? There was no quantitative risk assessment in terms of what those concentrations might mean in terms of risk to aquatic feeding wildlife, birds, mammals that might live in the area, and also what those body burdens that the fish and the mussels concentrated from the water, what the potential risk to those were. So that was one of the pieces we looked at in this report. And second, there's a very big data set of toxicity, and there was some toxicity observed. You know, the test looked at everything from toxicity to algae up through macroinvertebrates, fish, on into amphibians. There was no attempt made in the 2015 data to show what caused the toxicity that was observed in those tests. So we wanted to take a little closer look at that. Have the next slide, please. So again, just a simple graphic representation. What we did with the data is we started with the bioconcentration data, and we looked at a screening level risk assessment for aquatic feeding wildlife. So what does the concentration in the fish and invertebrate tissues mean for birds, mammals, and reptiles? And then we also looked at direct toxic effects from the body burden to both fish and invertebrates. And then we did the causative analysis for the toxicity data. Next slide, please. Okay, so what you're seeing here in the figure is a very simplified conceptual exposure model that we worked with in assessing the risk to the semi-aquatic birds, mammals, and reptiles. It's color-coded. The orange squares are data that we had available. The green squares are data that we had to estimate. So, you know, the source is obviously the Kissimmee River that's put in the ground in the ASR. Recovered water, we've got data for all of this, and we've got surface water data downstream of the discharge. We've got measured data for macroinvertebrates. We've got both lab and in situ data for that. We've got lab data for forage fish, things like fathead minnows and sunfish. We don't have data for the upper trophic level fish, the black crappie, the largemouth bass, et cetera. So we had to use some standard risk assessment bioconcentration factors to estimate that. But the whole point of this thing is to estimate what the exposure is to the birds, mammals, and reptiles. And that's what the equation that you're seeing on the screen is. And that's a standard risk assessment equation. What we try to do is estimate the exposure rate to those receptors. So we take the concentration of water and we multiply it by the amount of water, say a great blue heron is expected to drink every day. And then we add that to the concentration in each type of prey that the heron would eat times the amount of that prey type that the heron would eat. That's eventually divided by the body weight. That's the BW. And it's multiplied by a site use factor. In this case, we're looking at a really conservative estimate of risk. So we just assume that the great blue heron feeds only downstream of that Kissimmee River pilot test site. So the units for this equation, it's a rate, it's an exposure rate. So it's milligrams of a chemical per kilogram of a body weight for the animal per day. We can have the next slide. So we looked at that exposure rate for 13 different species, a whole range of bird species, representing a bunch of different feeding strategies, everything from dabbling ducks up through carnivores, piscivores, things like the osprey and bald eagle. We looked at two mammals. We looked at the raccoon, which is an omnivore that'll eat pretty much anything. And we also looked at a river otter that's going to eat some benthic invertebrates, some mussels, and some fish. And then we looked at exposure to an alligator. Again, this is a conservative approach. It's a screening level approach. In other words, we don't want to underestimate the potential for risk. We're only looking at ways to show that a chemical isn't isn't present in concentrations that are going to cause a risk. So we looked at maximum concentration. So of all the data set that we had from the discharge point for surface water, we picked out the maximum concentration of each chemical. We did the same thing from all of the fish tissue and all of the muscle tissue data. We then used no effect toxicity reference values. And what a toxicity reference value is, that's a TRV. It's the same units as that exposure estimate, but it's an exposure rate which has been experimentally shown to have no effect to the receptor. Okay, so it's a true no effect value. We also had some radiological data to screen that. We looked at the US Department of Energy's level 1 biota concentration guidelines, which are again are very conservative screening level values. The result of all of this is called a hazard quotient. That's the HQ there. What the hazard quotient is a simple ratio between the predicted exposure rate and the TRV, which is the no effect exposure rate. Where we have hazard quotients that are less than 1, where exposure is lower than the TRV, we can say with certainty that there's probably not a risk from that chemical to that receptor. Where hazard quotients are greater than 1, we can't say that. We're not saying, it doesn't necessarily mean that there's going to be an effect to that receptor, just that we can't screen it out using these conservative approaches. So can I have the next slide, please? So for birds, the 10 bird species we looked at, the mammal species we looked at, and the alligator, using this screening level maximum exposure approach, we had no hazard quotients that were greater than 1 for any chemical. So what that tells us is the likelihood of bioconcentration risk into the food chain and into the upper trophic level receptors is very low. Similarly, for the 2 radium isotopes we had data for, they were all less than the level 1 biota concentration guides. So the report concluded that while we still want to take a look at the bioconcentration of these things, particularly things that are bioaccumulators like mercury, selenium, things like that in the environment, we want to include all of this stuff in the future risk assessment, but we want to focus the risk assessment on those things that have a greater potential of being at risk to these receptors rather than kind of the whole suite of receptors. Have the next slide, please. So we also did the same thing with the tissue samples that we had. We found no effect concentrations for invertebrates and no effect concentrations for fish, and we compared them to the maximum detected concentrations of each of the chemicals of concern in each of those tissues. For fish, we showed that risk is probably de minimis based on the concentration. So even though some of the chemicals bioconcentrated and were at higher concentrations downstream of the discharge versus upstream, at least for fish, it showed that there's probably, those concentrations probably aren't problematic for the fish. For the mussels, we did have several that has hazard quotients greater than 1. For aluminum and molybdenum, we had hazard quotients greater than 1 both upstream and downstream, and they were at similar magnitudes of hazard quotients. That tells us probably that the ASR, the storage of the water, probably didn't have a huge effect. And the hazard quotients are going to be the same, both before the water goes in the ground and after it comes out. For manganese, every sample that we looked at had a hazard quotient of 1. That generally tells us we have a toxicity reference value for that chemical that's probably too low. So we don't know if it's an issue, but there's not much we can tell from what we have. So again, really low potential for risk due to direct bioaccumulation into mussels and fish. The report recommends that we continue to monitor these things based on the NRC recommendations of looking at potential for longer exposure or longer storage times and bigger release volumes. Next slide, please. And then the final piece of the historical data analysis is the causal analysis of toxicity. Like I said earlier, we have a big data set of toxicity tests, but there were no paired surface water samples with those tests. In other words, we see the toxicity in the test, but we have no mechanism to look at directly what might be causing those. So what we did was we went in and we looked at the big data set of water samples, and we tried to pull a water sample that was collected at either the Kissimmee site or the Hillsborough site corresponding to the tox test that was collected at the same day, on the same day. And we overlaid those water quality data as compared to aquatic water quality benchmarks. And we overlaid that with the toxicity test results. And what we saw is there was very limited overlap in the toxicity of a sample versus exceedances of any water quality benchmarks. So the data are a little bit uncertain there, but they really didn't support that the toxicity observed in the test was due to the water quality parameters that we had data available for. So moving forward in this, we recognize there's going to still be a need to do extensive toxicity testing. What we're recommending is that for each toxicity test, we have a paired water analysis for that test. So we know exactly what's in that sample, and hopefully we can tease out that data a little better moving forward. Next slide, please. So that was 2021. Now that we're into the new year and the new contract, we are working primarily on developing a comprehensive risk assessment work plan. Step one of that was reassembling the working group, which we've done. We had our first working group meeting just last week. We're going to work through the process of developing a plan to assess the risk down the road once we have these things up and running and the data are available. We're going to use this, the 8-step ecological risk assessment process from the US EPA. We're going to start on step 3. Steps 1 and step 2 are screening level steps. We don't really need to go through those again. We have the old data set plus all the bioaccumulation and the tox test information we worked on last year. So we're starting on step 3, and we're refining and updating the baseline problem formulation. You can see on the figure here where the working group is going to come in. They're going to be involved in the completion of the problem formulation and the study design, and looking at the sampling design as part of the risk assessment work plan. And then once we get the risk assessment done, we're going to ask the working group to take a close look at the results, risk characterization and risk management. Right now, we're just starting in the problem formulation step, and I'll talk a little bit more about that on the next slide, please.
5 minutes.
Okay, thanks, Anna. So this is a detailed flow chart of what's going to be in the risk assessment work plan, and we have 5 working group meetings. And this chart is laid out to show what we're going to cover in each of the meetings. They're color coded. So the meeting we just had last week is the red stuff. We took a look at what the risk management goals and risk questions for the risk assessment are going to be. And we looked at refinements to the conceptual site model. And that includes stressor sources. Where are the stressors coming from? Release mechanisms. How do they get released into the environment? What are the complete exposure pathways? Is there a pathway from that stressor to an ecological receptor somewhere in the vicinity of the well or regionally? And then taking a preliminary look at identifying the receptors of concern. The next meeting, which is scheduled for towards the end of July, about a month from now, we're going to look at the risk assessment endpoints. These are the assessment endpoints. What are we going to look at in the risk assessment? What receptors are we going to take a look at? Measurement endpoints, how are we going to measure that risk? And then we're going to look at refining the list of stressors, and that's where that data from the historical analysis we did last year is going to come into the work plan process. Third meeting, we're going to take a look at what the data gaps are, where are we missing data, and how do we start putting together data collection plans to fill those data gaps. And then the fourth working group meeting is where we're going to get into the risk analysis plan. We're going to figure out how we're going to look at exposure, how we're going to look at effects, and the risk characterization plan is how we're going to calculate and interpret hazard quotient calculations, and looking at how we're going to include those more advanced quantitative risk assessment techniques, the probabilistic techniques. Those aren't things that we probably need to do for every assessment endpoint, particularly those where we think we're going to have really low level risk. But for some things where there's some uncertainty as we bring more wells online, it makes sense to take a look at more probabilistic risk assessments to see how that might have a regional effect on things. So, and then the fifth working group meeting, we'll have a full work plan put together. The work group will be reviewing at that point. So next slide, please. Very little to talk about in terms of the actual work plan. This is one thing that we can talk about right now, and this is the updated conceptual site model. What this site model does is it shows what stressors are present and how they how they might have completed exposure pathways and what the receptors are. So in this case, like I said, we have physical stressors. It's a little different for a risk assessment, but we have a couple physical stressors. The release mechanism is how it gets from the source into the environment. In this case, the first one is in the groundwater recharge side. The stressor is localized pumping operations, and the exposure route is physical interaction with the intake mechanism. And the potential complete exposure pathway is the impingement and entrainment of ichthyoplankton. We also have potential temperature effects. So we're going to look at that, and that's going to be direct exposure to the released water. And we're going to try to look at effects to fish and non-fish populations and temperature dependent wildlife, things like manatee maybe. We also have physiochemical stressors, which again are a little different than the standard risk assessment, but these are changes to water quality, dissolved oxygen, pH, total dissolved solids, sulfates, things like that. These are direct exposures, and we're going to look at effects to fish and non-fish aquatic populations there. And then finally, on the right-hand side, when we get to the chemical stuff, which is the more typical thing we look at, again, there are effects to water quality from releases from the ASR. We're looking at direct exposure, and that's contact with the water. So those are toxicity tests, things like that. And then we're also going to take a look at ingestion of surface water for wildlife, for birds, mammals, and things. And then finally, we have the whole bioconcentration, bioaccumulation pathway, where we're going to look at exposure to food for these wildlife populations as the chemical might move through the food chain. And one more slide. So just to make things very clear here, the goals of this work plan are not to recreate, we're not going to reinvent the wheel here with the 2015 risk assessment. We want to expand that thing. We want to expand the results and conclusions of that thing and improve it a little bit to try to address everybody's questions a little better. We're going to incorporate the comments from that, and hopefully we can get some consensus from the working group on how to do that during this work plan. We want this thing to be regionally applicable. Right now, we're going to have data from the C38 well cluster, and Jen Mathia will talk about that a good bit in the next presentation. So we want to assess risk both at the vicinity of that discharge point, but we also want to be able to model the risks out regionally to see if there's any potential for risks on a larger scale. And we want this whole thing to be scalable. As you've seen in some of the previous presentations, there's a lot of different ASR clusters that are going to come online at some point. We want to make sure that this risk assessment will give us the ability to say that if there are similar conditions at those wells versus what we've tested in the ones that we have first here, then the risk is probably similar there. And that will allow us at some future date to take a look at what the unique attributes in those areas may be, so that we can focus the risk at those sites on those unique attributes. And that's all I have. Happy to take any questions. Thank you.
Thank you, Joe. Let's move on to our panel discussion session. Any questions for Joe?
I do not see any hands. Oh, sorry. Dr. Carragher, go ahead. State your comment.
Hi, Joe. Thank you for that presentation. I was just curious about the causal toxicity analysis for the tests. Was that primarily based on hazard quotient exceedances?
Yeah, so we pulled the water quality data that were as co-located as in both temporally and spatially for each of those tox tests as we could. We took a look at the chemical data in there compared to water quality criteria, ambient water quality criteria, chronic acute. If those weren't available, we looked at tier 2 stuff. And yeah, it was basic. Does the max concentration, or does the concentration in that sample exceed any water quality criteria? And then we overlaid that with the toxicity test result to see if there was any correlation between the samples that were toxic and any exceedances of water quality benchmark. And the data were really muddy. There wasn't a whole lot there that we can conclude.
Do you have any ideas about why that might have been the case for some of the observed toxicity?
Well, I mean, there were a lot of samples collected. And as you know, that sometimes you see toxicity in a sample and there's no way to know why. Maybe it was a bust at the lab or something else, but the toxicity was fairly limited in those tests. I think there were only 6 or 7 out of 80 or so samples that showed any toxicity. So it may be noise in the system. It may be something that just wasn't measured in those samples. It was impossible to tell from the data.
Thank you.
Thank you.
Okay, I don't see any other hands raised. So I think we can move on.
Thank you so much, Liz. Our next speaker is Jennifer Mataya. She is a senior biologist at the Environmental Consulting and Technology, and her presentation will be on the ongoing ecological studies along the C38 canal. And with that, I'm going to turn it over to Jennifer.
Thank you, Anna. Can everyone hear me?
Yes, we can.
Perfect. All right, next slide, please. So here is a timeline of the studies that we plan to do in support of the ecological risk assessment. The first phase that we are doing in 2022 is acquiring the data for pre-operational conditions. So prior to any of the cycling of the ASRs or the cycle testings within the C38 canal, we're going to collect some pre-operational data that will paint the picture of what the conditions look like prior to any ASR discharge. And this will be important to be able to compare the before and after conditions, and also help inform the ecological risk assessment part that Joe just presented on, saying if we see accumulations of certain parameters or chemicals within tissues of various organisms, we'll be able to understand whether these are pre-existing conditions or if this is indeed a response potentially to the ASRs. As well, in 2022, we are constructing a mobile laboratory similar to what was done in the previous regional ASR studies in early 2000s. We'll be conducting on-site bioconcentration studies using this mobile lab, and I'll get into that a bit later. And then supporting Joe in formation and PSI in the work plan development is another task that ECT is part of this year. Going into 2023, we will continue these pre-operational studies, looking to get at least a year of monitoring prior to cycling. Of course, everything's dependent on the ASR schedules themselves. While cycling is occurring, cycle testing of the ASRs, we will be doing those toxicity studies that Joe mentioned, as well as those bioconcentration and bioaccumulation studies. And then in 2024, we'll add potentially some mesocosm studies to really dive into the more longer term ecosystem effects. Next slide, please. So as part of the pre-operational studies, there are a number of components that we are taking a look at out there in the canal, all of which will be following a strict QA/QC program that we'll hear about shortly, and following DP and district SOPs where they exist. One photo I want to bring attention to in that are kind of similar to what we saw earlier today. Those two jugs up there are from 2007, I believe. The darker colored water being the canal, the C38 surface or recharge water, and the clear jug being the recovered water after it was recovered from the Kissimmee ASR. But you can see the stark contrast there. Next slide, please. As I mentioned, we will be following some work plans that are built upon the programmatic quality assurance plan. They will have specific SOPs associated with them, which are unique to each parameter, whether it's the periphyton or the ichthyoplankton. Each group will have its own work plan that we're working through right now that will be approved by the district. Next slide. As part of the general data collection and and per the SOPs, we will be collecting temperature data, in situ data pulled from YSIs as we're grabbing the samples. We have to get our collector's permits to sample those organisms. And of course, everything will be following and recorded in data forms provided in a database to the district. Next slide, please. So the sites that we're looking to monitor, these are our stations along the C38 canal. The goal was to establish stations that will be used not only for the pre-operational studies, but post-cycling as well. So these are, you could call them long-term monitoring stations within the C38 that will be held static as we go through the development of the ASRs. Each ASR well cluster has an upstream, a discharge, and a downstream station. So for the C38 North, we have the station 1 is upstream, station 2 is at the discharge, and station 3 is downstream. You note they're a little close together, 1 and 2, and that's due to the restrictions of the water control structure up there and the inflow from the other canal. And then at the Kissimmee ASR, which is directly across from the C38 South ASR, we have the same upstream, downstream, and discharge stations. We have also added 2 Lake Okeechobee stations. Station 7 is an existing long-term monitoring station of the districts, as is Station 8. Station 7 will serve as the kind of initial mixing zone of the canal water with the Lake Okeechobee. And then Station 8 is much farther out from the inlet or discharge location of the canal. And we'll be interested to see if there's any signature of the recovered water out there, but that's our other long-term monitoring station. Within the canal, we'll be looking at both banks. Understanding the canal is a trapezoidal, typical trapezoidal canal. There are distinct sides. So we want to make sure that we collect data on each side of the canal, understanding that as the water is discharged from the ASRs, the mixing zone of that water may or may not be bouncing from bank to bank as it travels down. So we want to make sure that our pre-operational studies are located, are well dispersed so that we can capture that discharge when the ASR wells are recovering. Next slide, please. So this is the schedule that we're looking at to conduct the studies. For the goal is to at least do a dry season, wet season. So at least two sample collection events. For water quality and periphyton, we will be collecting bi-monthly. For SAV, we will, our goal is to grab 3 events during peak growing season. Benthic macroinvertebrates will collect twice along with the sediment, apple snails, mussels. Fish population studies will occur 4 times. And then ichthyoplankton will be sampled monthly during the peak spawning season. Next slide, please. So for water quality, as Joe mentioned, it's really important to have paired water quality samples with any of your collection. And I like to think, I like to practice always grabbing water quality whenever I grab anything out of the water. So with that being said, every periphyton sampling event, we will be grabbing water quality. We will be doing water grabs for water quality analysis, looking at the metals and nutrients. These will be surface grabs from the first foot of the water. At each station, we are also going to have continuous monitoring using a multi-probe data sonde that will be looking at conductivity, temperature, DO, and pH. For the stations out in Okeechobee, we'll be relying on the monitoring that is currently continuously occurring at those stations. As well, whenever we're out there collecting samples, not only are we grabbing for analytes will also be taking the field measurements. So there's some redundancy there, but we want to make sure that if anything interesting is observed, we have the corresponding water quality data to go along with that. Next slide, please. As I mentioned, we will be sampling for periphyton. Periphyton is sensitive to changes in water quality, probably better than anything else that we could grab out there. So we've really ramped up the program in comparison to what was done previously. As part of the original ASR, we've added some redundancy in the number of periphytometers out there, increased the number of slides, and we'll be looking not only at taxonomy in the periphyton, but also chemical composition. So where metaphyton exists, so floating mats of periphyton, we will be grabbing those to analyze for chemicals and nutrients. And if those mats don't exist, we'll be collecting off the extra periphytometers that are out there to analyze the materials collected on those. We will be looking at different indices of the species there, taxa richness, diversity, et cetera, as well as cell density and abundance. This work is being supported or conducted in a large part by FIU and Dr. Geiser's lab. They'll be in charge of the taxonomy and the nutrient analysis. Next slide, please. We will be attempting to conduct some SAV studies. Now, of course, we recognize the canal is not prime habitat for submerged aquatic vegetation, but nonetheless, we want to be able to understand and document the existence of any SAVs that may exist, that may be out there in the canal. And this will be supplemented by the program that is occurring in the lake itself. And that's what that image is from, is one of an older lake survey grid. To begin with, we'll do the desktop to understand what species are out there, and then conduct a reconnaissance survey to help establish our plots for doing the mapping and the characterization. And for analysis, we'll be looking at the frequencies, species, density, et cetera. Next slide, please. Benthic macroinvertebrates. Again, these guys are important indicators of water quality. So we want to be sure we have a good established existing conditions for that community. We'll be doing this through deployments of Hesterdendi samplers, and those are the little discs you see on the top of the slide on the cinder block there. We'll have them out there for 28 days, which is corresponds to what we plan to do with the periphytometers as well. And we'll be doing taxonomic analysis and the diversity indexes as indicated there. Next slide, please. And while we grab those benthics, we're going to be grabbing some sediment samples as well. These will be in the form of grabs, 3 grabs per station, hopefully with a core, but we'll have our backup Ponar dredge if we can't capture enough in the cores. These will be analyzed for metals and nutrients as well, and we'll look at the composition of the sediment itself and take some measurement of sediment depth and water column depth at those stations. Next slide. Apple snails, we recognize the importance of snail kite to the whole system, and apple snails are an important part of the food, well, the only food source of the snail kite. So we will be taking collections of apple snails, not the native snails. We'll take the invasive ones and analyzing their tissues for metals, with the idea being that they will provide a before and after pre-operational versus during recovery analysis for the chemical composition within the tissues. Next slide, please. And we will do the same with some freshwater mussels. These are the same mussels that we utilized in the previous ASR ecological risk assessment. The Elliptio jayensis. So we will be using them the same. The idea is to collect resident mussels that may be out there. We'll be using a sand or a flea rake to pull them out of the sediments and analyze their tissues. We'll shuck them prior to shipping to the lab to analyze them for metals. Next slide, please. And finally, onto the fish. We will be doing some fish surveys, fish community surveys from a boat-mounted electrofisher. The goal will be to characterize as many fish that we can at each station. We recognize open water conditions like at station 7 and 8 are not very conducive to shocking. So we will supplement the information from those stations with the information that FWC is collecting. As part of this, we will also be doing a fish tissue collection program where we will select fish from 3 different trophic or feeding gills. The bluegill, crappie, and largemouth bass will be selected. We will homogenize tissues into composite samples and analyze for metals. Next slide, please. And then to understand the potential for impingement and entrainment, we will be doing ichthyoplankton tows. So, often we conduct oblique tows, which sample the entire water column in one tow. But in order to understand where the ichthyoplankton are congregating within the canal, whether it's which shore, how deep, etc., we will be doing 3 discrete tows, one at the bottom, one at mid water column, and one at the surface. This will help inform where potential intake structures should be located, help us to avoid sensitive nursing areas or nursery areas. And yes, so the plankton tows will be conducted during the peak spawning season monthly. And we'll be doing diel sampling, so both day and night sampling. Just one other thing, thank you, to add. We will be looking at, being that we can't tow through submerged aquatic vegetation, we will be doing qualitative assessments of any vegetation near the shoreline to just get a feel of what might be hiding in there where our tows can't go. Thank you, next slide. This is just what we'll be looking at. As I mentioned, we'll be looking at mussel or metals concentrations in the larger fish tissues. We won't be analyzing ichthyoplankton for any metals. And yeah, some just typical indices there. Next slide, please. All of this information will be summarized in bi-monthly progress reports. And once the year is done, we will compile a comprehensive pre-operational report for the C38 ASRs. Next slide, please. As I mentioned, we will be constructing, and we just put the order in for a mobile laboratory. The photos you see here of the completed lab is what I built last go around. So in 2007, and the photo there is it's sitting at the Kissimmee ASR. We will be designing or constructing a very similar, nearly identical model, building on some of the efficiencies that we discovered while running that during the last go around. Next slide, please. So this mobile lab will be used to run the bioconcentration studies. So it is designed to be able to park at each of the ASR well clusters with immediate access to the recovered water and the surface water prior to storage, so the recharge water. The mobile lab is designed to be able to do a mix of the recharge and recovered water. So it can do 3 different types. And we will be running bluegill and freshwater mussels. The collection will be sourcing the bluegill from a nursery and then the mussels from a local lake. Each group of organisms will be pre-treated, and that they'll be held at a lab in analyte-free water for a month prior to being run in the mobile lab. We will test the tissue concentrations prior to running them in the lab as a starting point, and then at the end of the exposure, which typically lasts 28 days. But may vary depending on the cycle schedules of the ASRs. Next slide, please. Kind of went over this. So yeah, we'll have the mobile lab done by the end of this year. And it is a flow-through system. Next slide, please. So not only do we do the tissue analysis, we will be looking and recording mortalities throughout the study. And with the mobile lab, it can be moved to different ASR locations as needed, depending on where they are in their cycle testing. Next slide, please. And in addition to the bioconcentration, which is the concentration of analytes from exposure to water, we will be doing the in situ bioaccumulation, which takes into account kind of the whole feeding. So not only being in the water, but also eating organisms that are also in the water with them. You've seen this slide a few times, I think, or this photo of this mussel cage set up. So it's designed to hold individual mussels in separate little compartments. I think it can hold 64. And we'll also be doing the paraphytometers that will be placed at those same survey locations that we saw previously as part of the pre-operational studies. But this time the intent is to put them in during recovery as well. So they'll be exposed to recovered water in situ in the canal. Next slide, please.
5 minutes.
Thank you. Additionally, we will be doing toxicity studies. Hydrosphere Research in Alachua has done these historically for us previously, and will also be conducting them this go around. They will be running the typical EPA methodology, as well as some additional ones, the FETAX, which is the frog embryo assay as well. We'll be looking to do these on varying lengths, varying recharge and recovery cycles as needed and as defined by the work plan that Joe had talked about previously. Next slide, please. Many of these studies will be required by the permits themselves, associated with the whole effluent toxicity as part of the MPDS and SERP permits. So some of them are regulatorily driven, others will be added if the need presents itself. Next slide, please. And this is from working through the working group discussions last year. The need was identified to maybe look at a longer term toxicity. So not just the typical acute and chronic that we know and that have been published, but to look at maybe a longer toxicity study that looks at reproductive success. So this is something we're working on with Hydrosphere to get a second generation result. So growing some fish, some fathead minnows to adults and spawning. Next slide, please. I believe that's it. Yeah. So any questions?
Thank you, Jennifer. So let's begin our panel discussion. Any questions for Jennifer?
I do not see any hands raised.
Okay.
I'm sorry, spoke too soon. Dr. Carragher has his hand raised. Please state your comment or question.
Hi, Jennifer. Thank you very much. I was curious about the water quality parameters you were measuring at the monitoring sites. Did you have organic contaminants you were looking at also?
So we currently, the list that we have, which is presented in the programmatic quality assurance plan as well, is metals and then nutrients.
Okay, thank you.
Mm-hmm.
Okay.
Any other questions?
There are no other hands raised.
All right, so let's move to the next slide. And we are going to take a short break, and we will be back at 2:15 p.m. Thank you. Welcome back, everyone. It's 2:15 p.m. So let's go back to our talks. Our next speaker is Steve Elliott. And Steve is a chemist at Stantec, and his presentation will be on the ASR Programmatic Quality Assurance Plan, which was finalized earlier this year. And with that, I'm going to turn it over to Steve.
Thank you, Anna. Appreciate that. As Anna said, my name is Stephen Elliott. I'm a chemist with Stantec and was tasked with putting together the Programmatic Quality Assurance Plan for the ASR program. Next slide. So for those who aren't really familiar with what a quality assurance plan is, QAPs really, and that's kind of what we call the QAP plans. QAPs describe kind of how project elements are done. We've heard a lot today about the science plan that was developed, and that really kind of goes into the who, what, where, when, and why kind of things are happening. Whereas a QAP gets more into the details of how project elements are to be done to complete those specific project goals that are established. The EPA has basic guidelines for QAP development that include project management, which goes into like problem definition and background, project organization, and data quality objectives, which we'll get into in a little bit. It also goes into data generation and acquisition, which goes into sampling design and methods, analytical methods and MDLs, and data management. Assessment and oversight deals with kind of the applicable criteria that may be involved, such as drinking water standards like we've seen throughout the day, and reporting requirements that would also kind of fall under that. And then validation kind of goes into the review, verification, validation, and usability, which each of those kind of increases in complexity and validity of the data as you kind of go through. So those are just kind of the basic elements for a general QAP. Next slide. However, with this project, since we're developing the QAP really early on, it became really apparent that we were going to have to take more of a programmatic approach. And so because we didn't know all the specific project details and what's going to be performed over the next, years and years and years. So we took more of a broader approach and tried to address all the anticipated activities that are going to be performed, but for those activities that aren't addressed in the QAP, we're going to rely on work plans to detail that kind of stuff. And we saw like with formation, they're still kind of working on their work plan. So they'll generally either reference procedures that are already detailed in the QAP, or they'll have to provide sufficient detail about those variances or items not addressed in the PQAP. One other kind of interesting thing about the PQAP, it's designed to be a living document. So over the course of the project, like I said, we started this very early. As we start to see more kind of routine things pop up, the district may decide to add those particular elements into the QAP as revisions. Things that are kind of done like one-off projects probably wouldn't fall into that category. But things, like I say, that get more routine will end up probably being included in revisions in the future. Next slide. All right, so the work plans, like we say, a lot of people have already kind of discussed developing these work plans, but we put in some specific requirements, kind of generalized, but just kind of basic guidelines for developing work plans that everybody needs to try to incorporate so that we weren't kind of missing things. So that would include defining the project scope and purpose, referencing standardized procedures and guidelines, or defining new procedures and guidelines as necessary. Justify the design strategy and sampling locations, discussing data quality objectives, and define parameters and analytical requirements, and reference or define equipment and procedures. For the data quality objectives, those for for those unfamiliar, it's really, there's some main elements to that. I think there's 6: precision, accuracy, sensitivity, which kind of goes more to kind of instrument capabilities for both field and laboratories, completeness goals, representativeness of samples, which kind of goes into like where sampling locations are and how representative they are of the surrounding areas. And probably the key one for projects this large is comparability, which is really kind of the guiding principle of this QAP, because you've got so many projects being done by different folks, different contractors, the district, over a wide range of things. We want to try to make sure that the data that's collected across all these projects can be directly compared to each other somehow. Next slide. All right, so the criteria that we set out, we started with, we had one UIC permit that we already had accepted and approved. And one of the guidelines was for drinking water criteria had to be met. So that's kind of what we use for the basis of developing the list of parameters that we have in the PQAP. It includes VOCs, SVOCs, metals, pesticides, herbicides, nutrients, radiological, even some disinfection byproducts. And so we focused more kind of on we provided in here in the PQAP, the Florida drinking water standards and EPA drinking water standards, both primary and secondary. And then also DEP contaminant target levels, which would apply to more of the groundwater and surface water samples, which will be collected more frequently than the drinking water. The drinking water will be primarily, I think, used for when we're doing water treatment and actually injecting back into the aquifers. So it's going to have to meet drinking water standards there. And then we also added, based on those standards, we suggested kind of recommended project MDLs that need to be met. So we included a list of all of those. So between the drinking water standards, we had kind of a list of over probably 100 compounds, but we also had a requirement to meet municipal wastewater standards, which has a slightly different list. And so we included that also in the PQAP. There's 2 tables for potential analytes. And again, for that second list, we put in the Florida CTLs and recommended MDLs. And so work plans will have to, pick and choose whatever they need to comply with and include this information here, or if they've got new analytes or proposing different MDLs, they will have to include that in their work plans and justify that. All right, next slide. So one of the big sections of the QAP is for field sampling. Most of this comes from DEP SOPs. If you Google FDEP SOPs, it'll pop up a big list of very comprehensive requirements and methods and techniques for all kinds of sampling activities. That includes kind of field forms and field logs. The forms would include like groundwater, surface water sampling forms. Logs would include, obviously your field logs, and then calibration logs, and even kind of equipment maintenance logs also have requirements. We go into equipment requirements, basic kind of sensitivity of the instruments that you're using, making sure that you're looking as low and as accurately as you can. We have extensive calibration procedures documented in there, as well as decontamination of the field measurement equipment, sampling equipment, tubing, even bottles if things have to be reused. And we go into quality control samples, which would include kind of your equipment blanks, field duplicates, some cases field splits, and even, maybe matrix spike dupe kind of extra samples that need to be collected. And we go into sample collection techniques kind of extensively. And here we For groundwater, we wrote sections on two main types of groundwater sampling that'll be done. And that's one kind of without pumps, which would include kind of the monitoring wells. So where you actually put a portable pump kind of down the well to collect the samples. And then also we included the SOPs and kind of summaries for wells with pumps, which would include kind of the larger ASR wells where they've got, dedicated equipment already on site, and you would do either spigot sampling or something to that effect. And we go into surface water sampling, which is fairly straightforward. And we reference these sediment and tissue SOPs, but because there are so many different ways that you can collect the sediment, so many different types of equipment and objectives that you're kind of going for, and the same with the tissues, we reference the SOPs. And so we're kind of relying on the work plans to really flesh out exactly what they're going to be doing and making sure that they are following those SOPs. We go into preservation and holding times. Also, we have a table of those. To do that, we had to kind of classify. I kind of organized, like VOCs, for example. We selected a particular method that would pretty much cover everybody's needs. And so because each different method has different preservation and holding time kind of requirements, so we wanted to at least give everybody a baseline to kind of work off of. So we did provide, methods, holding times, bottle types, and preservations for those specific methods. But again, if the work plans decide to use a different analytical method, then they'll have to specify whatever preservation and holding time requirements are going to be, that they're going to have to meet. And we also go into kind of chain of custody requirements for all the samples kind of collected. Next slide.
5 minutes.
Okay. Laboratory certification. So for the chemical analysis, we're shooting for everybody to have all the labs that are utilized to have T&I certification, but that may not be the case for some of like the isotopes or some of the mineralogy stuff that you've seen today. But when available, we're shooting for having T&I certification. We go into detection and reporting limit requirements, quality control requirements, which go into laboratory blanks and control spikes, matrix spikes, things like that. We have a list of reporting requirements for the project and also laboratory storage requirements. Next slide. So for data assessment, we did include a section on literature assessment, which I think is very key. We've seen a lot of people today kind of referencing, older studies and projects to get data from. And so we do kind of highlight, procedures to review that to make sure that it is valid and, to assess data gaps, that kind of thing. We do have a section on field data validation, which is fairly straightforward. And then we do a laboratory data assessment, which is a bit larger, goes into data validation and then usability summaries, and then how all of the qualified data would get imported into ADAPT and then ultimately DB Hydro. Next slide. So the well construction, there's really not a formal QA program for that, but there are numerous standards, rules, and regulations related to these activities. So we included kind of a list of ASTM and AWA, there's quite a few of those. But we have a kind of an extensive list, and there again, we'll kind of rely on the work plans to detail exactly what they're doing and what guidance they're following. So an observation would kind of include observing project progress, inspecting materials to spec, and identifying safety hazards. All right, next slide. So hydrogeological monitoring, there's going to be several kind of benchtop surveys done initially, as we've kind of heard about today. But then there's also going to be some on-site testing, data collection events for surface geophysical, tracer testing, pathogen activation studies. There are no standards that we could find, ASTM standards for these. So the work plans, again, will have to really kind of flesh out what exactly they're doing and what their goals are. Next slide. Ecological monitoring, we just saw Jennifer's wonderful presentation about a lot of this stuff. We do have guidance in the QAP for EPA actually has guidance on mobile lab construction. So we included kind of a summary of the key aspects of that. Operational considerations would be kind of the list of testing organisms and foods that'll be used, food quality. And the other stuff I think is really kind of already kind of addressed by Jennifer, but these are all kind of touched on in the PQAP, but again, it's really relying on the work plans to detail all of the specifics of each of these. Next slide. All right, one of the key parts of the QAP is kind of data management. And so we go into kind of how the data is going to be stored, which will be typically in DB Hydro or eventually into Morpho, which is managed by the district. Custody goes into kind of protects the information's integrity. It's where only the PMs can revise, data once it's validated. Security would be to protect the servers from fire, theft, loss, degradation. Access would include, making sure that the public has access to certain things, or the district, not everybody may be able to see everything. So we want to make sure there's a level of access. And then archiving procedures for all the data that's stored and how long we're going to keep it are kind of included in there also. And then one more. And audits. This is really kind of the principal means to determine kind of compliance with the QAP and all the work plans that we're doing. So these should be done periodically. Field audits typically kind of done annually or something like that. DEP has got a lot of good checklists that we can use. Laboratory audits are suggested, like if you're bringing on a new lab, it may just be kind of a benchtop, but if through validation you see some kind of systemic issue, you may want to do on-site laboratory audits. And then data management audits are also critical to make sure that we're checking the security and custody and storage access. All of that is up to snuff. And obviously, if there is any kind of non-compliance issues, we would get into a corrective action kind of situation where we detail if, what would be needed in a plan for corrective actions. All right, next. And so just to kind of wrap everything up, it's really designed to guide future work plans, which I just kind of said repeatedly throughout the document. It's, like I say, it's going to be living, it's going to be probably revised, probably more than, usual in the first couple of years as we determine, what's going to be more routine. And then, it goes through potential parameters, sampling analysis, well construction. We cover quite a bit in the PQAP. So with that, I think I'm done.
Thank you, Steve. And now we are going to move to the panel discussion session. Any questions for Steve?
I do see one hand raised. Dr. Carragher, go ahead and state your comment or question.
Yes, thank you, Steve.
Sure.
I was just curious about the eco-toxicology. Did you say that was covered under the quality assurance plans?
There is a relatively brief section, but we're going to really rely on ECT to provide most of that information in their work plans.
Okay, great. Thank you very much.
Yes, yes.
Any other questions?
I don't see any other hands raised at this time.
Okay, thanks, Liz. So now we are going to move on to our next presentation by our invited speaker from our sister agency, Southwest Florida Water Management District, Sammy Smith. So Sammy's presentation will be on the recharge projects led by the Southwest Florida Water Management District. And with that, I'm going to turn it over to Sammy.
Hi, good afternoon. My name is Sammy Smith. I am a staff hydrogeologist in the Water Resources Bureau Water Supply Section at the Southwest Florida Water Management District. I'm here today to give a brief overview of some of our cooperatively funded recharge projects, many of which are specifically aquifer storage and recovery, although we do have several others that are direct aquifer recharge projects, which I'll cover in a bit of detail because of their scale and importance. Among those is the Flatford Swamp Aquifer Recharge Project, which is not itself a cooperatively funded project. It is funded solely by the district, and I happen to be the project manager of that one. Next slide, please. The Cooperative Funding Initiative is a district program that allows local governments and private entities within our 16 counties to share costs for projects that aid in creating sustainable water resources, providing flood protection, and/or enhancing conservation efforts. In evaluating the project applications that come in for recharge projects specifically, we pay really close attention to how they align with our district's strategic plan. That is, we have regional priorities that in large part determine where our recharge projects get funded. These priority regions include our water use caution areas and our most impacted area of the district. Now, when these cooperators apply, we evaluate the potential benefits and the viability of their proposed projects, and then we determine if they will be recommended to our governing board for funding. Once their projects have been approved for funding, the district has historically covered up to 50% of the overall project cost. Next slide, please. The types of projects that come in the door can be highly variable, but these, as you can see, are just some of our current and past projects in the realms of aquifer recharge and ASR. While I won't have ample time to go over each of these in individual detail, I will highlight some of the ones that I currently manage and myself I am familiar with. As you can see by these lists, we do have several that have either been funded in the past or are currently funded and are underway in some capacity. The map to the left, it doesn't show the location of each individual project, but it does highlight the counties where these projects are located or are planned for. And as you can see, many of them are in our more coastal and populated counties. Next slide. This map is just a more zoomed in view that does show where several of our projects and their various locations are pinpointed. Next slide. I'll start off with some of our more notable ASR projects before I move on to a couple of our larger direct recharge projects that I currently manage. The first up is going to be the City of Northport ASR project. This project is located in the City of Northport at the Myakkahatchee Creek Water Treatment Plant, and it dates back to fiscal year 2017. This part of the project is an extension of the original project whose funding history with the district actually dates back to 2009. So this project is one that has actually been around for quite a while. The ASR facilities under this more recent phase are intended to provide the ability to increase use of alternative water supply by providing storage for harvested stormwater and excess surface water flows from the Myakkahatchee Creek during the rainy season for later use in the dry season. Now, this ASR provides the means to store and ultimately to recover large quantities of water for both seasonal and long-term use. It's water that would otherwise be unavailable due to land limitations and cost. For example, an above-ground storage tank that they priced for this phase of the project, which is just 2.5 million gallons at the time, was estimated to come at a cost of $3 to $4 million. And like most things these days, that cost has probably greatly increased since 2017 or 2018. And that cost of $3 to $4 million doesn't actually figure in any of the electrical work, piping, land, instrumentation, or other costs. The previously proposed storage volume of the ASR well by the city was 30 million gallons, which is 12 times that capacity of 2.5 million gallon tank that I previously mentioned. And during their cycle testing of the well, they actually did look at the potential for expanding the size of the ASR storage bubble. This particular ASR project was originally developed with a zone of discharge concept and operational testing permit, meaning that they were not required initially by FDEP to meet primary drinking water standards prior to injection. And this was the case during their various cycle tests that included multiple rounds of injection and recovery. And the city did have favorable results associated with the die-off of coliform bacteria in those cycle tests. Next slide, please. These figures are from their most recent cycle test, which is 6C. This was between the end of July and beginning of August 2021. Now, what these show are the highest or starting concentrations of microorganisms recorded during recharge prior to injection at the head of the ASR1 well. The figures for each microorganism show that there is notable die-off in the storage zone at ASR1 after 3 days of storage. Microorganism sampling was conducted after 3 days, 7 days, 14 days, and 30 days of storage, respectively. The initial sampling plan for cycle test 6C, it only required sampling of the recovered water after the 14 days of storage. However, the city did take extra steps to continue sampling for microorganisms after 30, 60, and 90 days to better round out their data collection and help provide them with a better reflection of how the system could functionally operate. You can see in this first figure that the coliform count was initially at 7,270 units per 100 milliliters, and that by day 3 of storage, that count dropped to 30 units per 100 milliliters. By day 7, it was down to a count of 2. By day 14, it was non-detect. There was a similar pattern for the fecal coliform, which you can see at the bottom in figure 2. The starting count was at 370 units per 100 milliliters. By day 3, that was down to a count of 3. By day 7, it was down to 2. And by day 14, it was at non-detect. On the right side in figures 3 and 4, while they don't have starting counts shown on these figures, you can still see that between days 3 and 7, the counts dropped substantially for both E. coli and HPC. And for anyone who might not be familiar, HPC refers to a heterotrophic plate count, which is a term used to refer to the standard plate count. And that's a procedure for estimating the number of live heterotrophic bacteria in water. I believe the standard for potable drinking water, according to the CDC, is less than 500 CFU per milliliter. And you can see that by day 7, they surpassed this at 63 units per milliliter. Next slide, please. Finally, on this slide, they did include in their test results the enterococci virus and its gradual inactivation over the course of 30 days of storage. Now, it's known to have a longer period of inactivation than coliform, of course, and there's a bit of a step back that you can see around the 14-day storage period, but the consultant said they thought this to be an anomalous result. All in all, they had impressive cycle test results. However, due to recent permitting changes with FDEP, the city now is currently exploring new treatment options, one of which is chloramination, much like what's being done at Peace River and some other facilities with similar source water quality. And they will be deciding on how to proceed with revising of their current infrastructure to accommodate the UIC permitting requirements to meet primary drinking water standards at the wellhead. Next slide, please. This project is also one of mine, which I currently manage under the umbrella of our cooperative funding initiative, and it's an interesting one. The first year of funding for this one dates back to fiscal year 2021, which is for 30% design and third-party review of an ASR system to store and recover reclaimed water, which is excess surface water from Lake Tarpon, as well as an aquifer recharge system designed to help restore water level elevations in the northern Tampa Bay water use caution area. And it's also intended to aid in aquifer freshening. There will be a shared intake structure for both wells, and it is the intent of Pinellas County to only pool and utilize recovered quantities of water from Lake Tarpon when it is in excess. And what that means is when the water is actively flowing over the outfall structure in the rainy season. The wells and surface facilities will be located at Chestnut Park in Palm Harbor on Lake Tarpon. And their plan is for a minimum 5-year total recovery quantity of 300 million gallons for the ASR portion of the project, as well as 1 billion gallons of minimum recharge volume over a 5-year period for the aquifer recharge portion of the project. This project, it could also potentially provide a reduction of nutrients going into Old Tampa Bay. The ASR well and associated monitoring wells have already been constructed. The county plans to eventually proceed with design of surface facilities as the next phase in this project. They've also recently been given permitting related direction by FDEP and are currently in talks with UIC permitting folks to determine what the outcome of that will be. The original concept for this project was also zone of discharge, and the aquifer recharge well is planned to be drilled into the non-USDW in the aquifer. The county has most recently received direction that they will need to meet primary drinking water standards at the well for both the ASR and the aquifer recharge components. And so they're currently in internal discussion as to how they'll progress and whether that will alter their original design and construction plans. Next slide, please. The next project I'll talk about is the South Hillsborough Aquifer Recharge Program, or SHARP, and it includes a series of both constructed and planned reclaimed water recharge wells that are located in Hillsborough County along the eastern shore of Tampa Bay. This is nearly at the center of our district, which you can see signified by the red dot on this inset map to the left. The benefit of this project is to expand the use of reclaimed water to recharge non-potable portions of the upper Floridan aquifer. And that's to help improve aquifer level conditions in the most impacted area of our southern water use caution area in our district. And this is an area where saltwater intrusion is of particular and growing concern. The program currently has 3 phases. Phase 1, which you can see represented here in the light aqua color on the map to the right. This included construction of RW1, which is a 2 million gallon per day recharge well, and its associated monitoring wells and infrastructure. And this well site has actually been actively operating for over 7 years. To date, it has injected more than 5.5 billion gallons of water into the upper Floridan. Phase 2, which you can see represented in white, this included the construction of RW2 and RW4, also each with their associated monitoring wells and infrastructure. RW2 has been operationally testing since early 2021, and the county anticipates applying for an operational permit sometime in August of this year for RW2. Phase 3, which is represented on this map in yellow, includes the planned construction of RW3, RW5, and RW6, the last of which is not shown on this map because its location has yet to be finalized. But a total build out, including all 6 recharge well sites, SHARP will have the potential to provide upwards of 12 million gallons per day of recharge into the most impacted area of our district, as well as potentially provide for future consideration of indirect potable reuse. Next slide, please. I just wanted to show this figure quickly, generated from phase 1 data from RW1, which is the first SHARP recharge well. What this shows is groundwater level versus recharge volume over about 6 of the 7 years of their operation. The orange, yellow, and blue lines here all represent groundwater levels in monitoring wells associated with phase 1. However, the blue line in particular shows groundwater water level data from a recharge zone monitoring well that's located about 1,200 feet from the recharge well. As you can see along the bottom axis, this is showing recharge over time, spanning from August of 2015 to June of 2021. And at the beginning here on the left, you can see that the groundwater level elevation was drawn down below 0, hovering probably around -4 feet or so. But if you fast forward to 2021 on the right, you can see that they're seeing around a 25-foot head increase in this recharge zone monitoring well, which again is about 1,200 feet away. Next slide, please. This one is one more quick figure from phase 1 of SHARP, which is based again on data from RW1. If you pay attention to this sort of red line, which is associated with the recharge zone monitoring well, you can see here that the TDS in the recharge zone in the upper Floridan in this area was well above 30,000 TDS when they began injection. But after several years of injecting at RW1, you can see that that's come down considerably, and they're now actually below 2,000 TDS, which shows some pretty substantial freshening of that recharge zone surrounding the well site. So On this project, we're excited to see what additional data and results come out of this next phase, which is phase 2, with the addition of those two MGD recharge sites. Next slide, please. Finally, this brings me to one of my biggest projects, and I decided to talk about this one today because it's an important one for the district, and it's got a lot of interesting background to it. Plus, it's unique in that it's solely funded and overseen by us here at the district. And I just recently took over as project manager when Lisanne Morris retired. The district owns some 235 acres, commonly known as Flatford Swamp, which are located in the upper Myakka River watershed in eastern Manatee County. This little neon green shape at the top here is Flatford Swamp. And the inset map to the right, that denotes that same area, but this is the district's actual property boundary. Next slide, please. The pink square on this map, this denotes our current recharge test well project area. Next slide. This acreage is also directly in the midst of our southern water use caution area of the district, and also directly to the east of our most impacted area, or otherwise called the MIA. Flatford has been impacted by excess water flowing from multiple upstream tributaries that have seriously affected the swamp's hydrology for a number of years. Now, one of the major factors is that these excess quantities, they infiltrate during the dry season, and that serves to alter the normal river floodplain hydro period. So in other words, it's staying overly wet, both when it should be and also when it should not be. Now, the most obvious consequence that we've observed in relation to all of this excess water is abnormal tree mortality, and more specifically, the die-off of hardwood species. And we began to receive reports of that back in the 1980s. We've estimated using integrated modeling that on an average annual basis, there are still approximately 10 million gallons per day of excess water that impact the swamp. Next slide, please. So you might ask, where does all this excess water come from? Now, as I mentioned, there are multiple tributaries that flow into the swamp, but this is also in the midst of a predominantly agricultural area. And while the district has worked for many years with surrounding farmers on various farms projects to implement best management practices, there's still excess water and still a number of other factors that are at play in this area. The area geology and geomorphology here is pretty unique. And that is to say that about 5 to 8 feet below the land surface here, instead of having nice, deep, sandy, unconsolidated sediments that are well draining, you have what's called a hard pan layer that consists of compacted organic matter and clay. And this actually impedes water in the swamp from draining or dispersing more quickly into the subsurface. Now, if you combine that with the fact that the swamp is pretty substantially topographically lower than the surrounding land surface, it tends to fill up a little bit like a bowl. Next slide. So what do we do about it? Obviously, we would like to reduce the excess water in the swamp and begin helping to trend it back towards its natural historic hydro period. But as we also know, one of the ongoing issues in the SWCA and the MIA is the significant reduction in groundwater levels in the upper Floridan aquifer that have occurred as the result of groundwater withdrawals. But we believe that if we can divert some of this excess water from the swamp and use it for aquifer recharge injection, that we could potentially supplement the upper Floridan aquifer and also contribute to increasing the groundwater levels in the area. Now, this has the potential to aid us in meeting our saltwater intrusion minimum aquifer level, or SWML, which has been established for the MIA, and along the same lines to potentially aid in the mitigation of future saltwater intrusion in the area. Aquifer recharge, after exploring a multitude of other options, is just what we determined to be our best option out at Flatford. Next slide, please. I'll give a brief review of what our previous project concept was and how it's sort of changed over time. As some of you may know, our original plan at Flatford was to explore the concept of in-ground filtration using a zone of discharge test permit. Our original concept was to explore minimal treatment and to allow for natural in-ground filtration in the aquifer over a distance of about 1,000 feet to our compliance well. You can see the infrastructure map. It's a bit small and crowded on the right here, but if you look down at the bottom right-hand corner, you can see recharge well 1. That's where our actual recharge well is located. As you move up the line from that, you can see we've got 3 monitoring wells, 2 which are in the injection zone and 1's in the Sewanee limestone, which is a more shallow monitoring well. And then up over to the top left, you can see Taylor Road. If you see, there's sort of a pipeline that runs along this little tributary coming off of Taylor Road. That's the Myakka tributary where our intake structure is located, where we are actually diverting water coming into the swamp. So our original concept, as I said, was zone of discharge, and it was to use minimal treatment and allow for that natural in-ground filtration in the aquifer to the compliance well. And at the time, that minimal form of treatment we proposed consisted of sodium bisulfite, or SBS. And what that is it's an effective food grade oxygen scavenger, which has some ancillary disinfection properties. Its primary function, though, was to remove dissolved oxygen and to aid in mitigating mobilization of arsenic in the aquifer. So the original concept to our governing board in 2017 and requested funds to construct this first test well site. And we chose this site off of Taylor Road because number 1, it's already owned by the district. But number 2, we also saw the potential for a good zone of discharge site there. In 2017, we also obtained our permitting for this test well for construction and operational testing. And then in 2019, we actually drilled the wells. We did testing to ensure that we had a suitable zone for recharge here. And when all of the findings came back satisfactory, we moved ahead with our additional design and permitting. The target capacity for our current and only test well is 2 million gallons per day, which is the max quantity that we'll be diverting. That volume can and will fluctuate below 2 MGD, and that will be based on seasonality and other factors that we observe during our operational testing. Most of the infrastructure was completed and in place already when in May of 2021, we did receive permitting changes from FDEP. They no longer wanted us to continue with the zone of discharge concept, and instead they required that we treat the source water to primary drinking water standards. So we began to look at some of our other potential treatment options. And what this led us to was a study by Hazen and Sawyer at Peace River. And they were using chloramination. And because they have similar quality source water as we do at Flatford, we decided to pursue chloramination along with sodium bisulfite as our new method of disinfection. One of the reasons chloramines are favorable for us versus just straight chlorination is because we do have notable total organic carbon content. And we wanted to explore a treatment option that helps us to reduce the potential for disinfection byproducts. So once we decided on this new course of action, we took our plan and our newly proposed treatment train, along with all the costs associated with the changes to the infrastructure, to our governing board. And this was back in December of 2021. We were able to get them approved. So as for now, the aquifer recharge project at Flatford remains on track. We did just have our pre-operation inspection with FDEP and received clearance. We are in the startup and testing phase currently, and we remain optimistic that we'll be able to begin operational testing late this summer, which of course is rapidly approaching. So with that basically wraps up my presentation on some of the recharge projects I'm involved in here at SwiftMud, and I would be happy to answer any questions. Thank you.
Thank you so much, Sammy. So actually, we're going to move on to our panel discussion. And during the time, panelists will be able to ask questions. So basically, to any speaker. So, are there any questions for our speakers?
Dr. Tom Messmer, please state your comment or question.
Yeah, there is some information that just came out today that could have some serious impacts on virtually every ASR or MAR project. The EPA ruled this morning that they intend to make all PFOA, PFOAS, and all the forever chemicals free from in drinking water. In other words, essentially zero concentration. So therefore, drinking water standards for injection that have to meet potable standards will have to show technology to eliminate these compounds totally, which would have pretty broad implications on the economics. Any comments on that issue?
Well, hey, this is Bob Verastro. That's interesting, Tom. Thank you for sharing that. Obviously, the treatment technology evaluations that we've been conducting to date have not considered, I'm quite sure, any and all of the constituents, whether if there are new constituents that the EPA is now adding to that list. We certainly have not evaluated them in our treatment studies to date, I don't believe.
No, I'm not aware of any research to that in terms of our recharge projects either. I do know it. I am aware that PFAS have been of a growing concern, and anticipated that would be coming along.
Okay, Dr. Renee Price, please state your comment or question.
Yeah, so I guess I have a comment that will turn into a question, but I'm aware that one of the cities in West Palm Beach is looking to switch from their water supply from surface water to potentially using the upper Florida aquifer as a water supply. And I'm just wondering if you are aware of that and if there's any concerns that the ASR wells could interfere or interact with that city of West Palm Beach potential use of the upper Florida aquifer.
Well, I'm generally familiar with where the city's ASR well is, right on the shores of Clear Lake at the city's water treatment plant. I'm not aware of where the city intends to construct what would be a new water supply well field with the Florida aquifer. So it's kind of hard to determine how close or the operation of their ASR well could have on a future Florida aquifer supply well field. I do know that the upper portion of the Floridan at that area of West Palm Beach is got a total dissolved solids concentration of somewhere between 5,000 and 8,000. So the city will definitely have to have a membrane treatment process that's going to be able to have the chloride concentration be within drinking water standards. But no, I don't know anything more about where the city's Florida well field would be proposed at this time.
Is it expected? Is it expected though that the city would have some conversations with the South Florida Water Management District?
Oh, for sure. Yeah, that would definitely be something that we'll hear of if the city formalizes a plan to do something like that. Certainly, that'll come into our regulatory group for permitting, for sure.
Great, thank you.
Any other questions for our speakers?
I don't see any other hands raised at this time.
All right, so we are going to go ahead and move on to the public comment session. And please remember to raise your hand, and Liz will call your name in the order they appeared.
Okay, first up, we have David Pine. His hand was raised. Okay, since we don't hear David speaking, we're going to move on to the next commenter, which is Mark McNeil. Go ahead and state your comment. And you're currently, okay, you're unmuted now.
Can you hear me okay?
I can, yes.
As a back, I've got a few comments of my own, but I do have David Pine's comments. He forwarded those to me and asked me to read them if he wasn't able to be heard again. I don't know how you'd like to proceed, if you'd like comments or David's or both.
We'll take both.
Okay, let me start with David's comments, and I'm reading this off of a prepared statement by David. David's president of ASR Systems in Gainesville. David says, an important key to the success of any ASR program is to start small, learn from early, small phases, and integrate that experience into the design, construction, and operation of later phases. That is not the path that we are currently on. Instead, we are on a path to construct and cap many of the planned 55 ASR wells and monitoring wells, while a very large 50 MGD water treatment plant is designed and constructed capable of meeting all primary and secondary drinking water standards in the recharge water before any cycle testing can begin. That treatment plan is currently scheduled for completion in 2026. Cycle testing would then begin, but it would likely be about 2029 before cycle testing data becomes available to evaluate whether the well design or the treatment plant design is appropriate. By then, we will likely have spent between $500 million and $1 billion. Next paragraph, the first ASR well at C38 South will be available to start cycle testing within the next 3 months, but instead it will likely be capped pending treatment plant construction. We need to start cycle testing now, not later. We urge the South Florida Water Management District, the Corps of Engineers, and DEP to authorize interim cycle testing to proceed at the first 2 to 4 ASR wells at C38 South, using interim treatment facilities that would include simple screening, filtration, and disinfection with chloramine. This would be similar to successful ASR operations at Marco Island during the past 10 years, planned operations at the Peace River, Minnesota ASR well field, and planned operations at the Southwest Florida Water Management District Flatford Swamp Recharge Program. It is also similar to ASR cycle testing in what is now called the Avon Park Permeable Zone, conducted at L63 North back in 1989. At this initial relatively small scale and short duration, any ecosystem risk would be minimal. The benefits would be substantial, including improved understanding of well and aquifer hydraulics, such as any movement of water through confining layers during recharge and recovery periods lasting several months, subsurface microbial and geochemical processes, calibration and verification of aquifer hydraulic models and geochemical models, recovered water quality, and associated ecosystem effects. I recommend that the peer review panel consider making a specific recommendation to South Florida Water Management District, Corps of Engineers, and DEP to authorize interim cycle testing to proceed now, not years from now. This would provide for preparation of plans for the associated relatively simple facilities and permitting in parallel with current activities associated with the permanent treatment facilities. Thank you. And that concludes Mr. Pine's comments.
Okay, and do you want to go ahead with your own?
Yeah, can I take a real quick deep breath?
Oh, yeah.
Okay. All right. I've got a couple of thoughts here I'd like to share with the group. By the way, I'm Mark McNeil with ASRS based in Tampa. The level of treatment, I believe, should be commensurate with the storage zone water quality. Brackish groundwater requires membrane treatment, which we confirmed today effectively removes coliform bacteria. We do not use one treatment technology to treat freshwater, groundwater, brackish groundwater, and saline groundwater. So why would we consider one level of treatment across the multiple injection zones or storage zones that we're considering? To color removal to the secondary drinking water standard of 15 color units should not be a treatment goal regardless of the receiving zone water quality. Secondary drinking water standards are by definition not health-based standards. In fact, they are not even regulated by UIC at the federal level. Color attenuates quite rapidly and is not conservative in the groundwater, and this can be demonstrated further during future cycle testing at these sites. 3, we need to apply the scientific results we develop. I have a great level of respect for Dr. Lyle and the numerous studies he has had. He has led over the past decade or more. If we don't take his results from the controlled field and lab studies and confirm them with the pilot scale testing at these sites to confirm coliform die-off in the subsurface, we are doing a great disservice to his scientific findings. At that point, his brilliance is no more useful than that of the professor on Gilligan's Island. And finally, number 4, keep in mind that the 3,000 milligram per liter TDS ambient groundwater is an important regulatory threshold. EPA places a higher level of protection on less than 3,000 TDS aquifers by requiring a major aquifer exemption, whereas greater than 3,000 TDS aquifers can obtain minor aquifer exemptions at the regional level. Minor aquifer exemptions are a common regulatory relief mechanism across the country and could certainly allow us to temporarily cycle test using partially treated surface water containing some coliform bacteria in greater than 3,000 milligram per liter TDS aquifers to confirm the scientific findings over the past decade or more. And that concludes my thoughts. Thank you.
Thank you. Thank you for your comments. Is there anyone else from the public that would like to state their comment? Okay, at this time, I do not see any hands raised. So that concludes our public comment period.
Okay, Liz, so we can move on to the next slide.
Okay, all right, so this is our last presentation of the day. It will include expected progress over the next year, closing remarks, and expectations for the peer review panel. This discussion will be led by Anna Washnika, our lead scientist and project manager of the science plan. And June Marecki is going to be replacing Bob Verastro. He was going to present on a few slides, but he's passing the baton to June. She is lead geochemist from the Corps. And then I'll wrap up with final closing comments. So with that, I'll pass it over to Anna.
Thanks so much, Liz. And let's move on to the next slide. Okay, so I'm going to first give an overview of the studies that will be conducted over the next year and in upcoming years. So the blue color on the schedule indicates studies that were completed in 2021, while the green color indicates studies that are either ongoing or are currently being developed. We currently have 8 ongoing studies, and we are either developing or reviewing scopes of work for additional 3 studies at this moment. And today we gave you an update on the progress of optical borehole image logging, bioclogging, geochemical analysis of the cores, multi-well assessment of fracture porosity, ecological risk assessment, pre-operational ecological monitoring along the C38 canal. We are currently reviewing a scope of work for the mixing zone modeling, and 3 more scopes of work are being developed for evaluation of the arsenic mobilization and buffer zone, and for conducting surveys of radium occurrence. Next slide, please. Now I will give a short overview of the activities associated with ecological risk assessment. We are currently in phase 2 of the process. We are developing a work plan for completing quantitative ecological risk assessment, which Joe Allen talked about today. And once we finalize the work plan, later this year, we will switch to phase 3 of the ecological risk assessment process, which is the collection of the data needed for completing the quantitative ecological risk assessment. And as Joe already mentioned, this is done in collaboration with the group of subject matter experts from our partnering federal and state agencies, and also local research universities and non-governmental organizations. And the reports produced during the first phase of the process, which Joe also mentioned during his speech, include a scoping document and preliminary quantitative ecological risk assessment analysis based on the historic data. And these two reports are included as appendices in the 2022 ASR science plan, which will be released later this year. Next slide, please. Also, as Jennifer Mataya already mentioned today, we designed a mobile lab area this year, and we will construct it hopefully by the end of the summer. So we should be able to conduct the first bioaccumulation studies using source recovered mixed water in 2023. I should emphasize that the timing of this and other types of ecological studies that we will be conducting is closely linked to the construction schedule of the aquifer storage and recovery wells, since we will need the water from the wells to conduct the experiments. So the first well should be completed along the C38 canal sometime next year, and that's where the first studies will take place. Next slide, please. In late 2023, we are also planning to begin construction of the Mesocos facility at Kissimmee River ASR. We are planning to conduct different bioaccumulation studies at this facility involving different types of organisms in the following years. So we will also look at the effects of recovered water on freshwater community structure. So all of that will be done most likely in 2024. And details on these studies will be provided at the future ASR workshops. Hopefully, we can provide some details on those studies next year. Next slide, please. We are also planning to conduct mixing zone modeling this year. The scope of work, well, maybe let's start first. Okay, so the mixing zone modeling, but before we go there, we're also going to conduct long-term pre and post-operational monitoring along the C38 canal. And just like Jennifer mentioned earlier, this will be part of the before-after control impact studies, and that will begin this year. And we will continue with post-operational studies once the cycling begins. Next slide, please. And also, so I already actually talked about that. So these are our mesocosm experiments that we'll be constructing at Kissimmee River ASR in 2023. And so that should allow us to start the experiments in 2024. Next slide, please. And now the mixing zone modeling. The scope of work is currently undergoing an interagency review by subject matter experts. And the mixing zone modeling will help us evaluate the potential impacts to surface water quality resulting from inflows from ASR wells into the adjacent canal systems and farther downstream. So this modeling is needed to determine the impacts at the discharge points and the subsequent dilution or mixing that will occur downstream. So this modeling should provide us with additional helpful information on the possible spatial extent of the impact associated with the discharges from ASR wells on water quality and biota in the adjacent aquatic systems, meaning the canals and farther downstream in northern part of the lake. And with that, I will turn over to June.
I'm not sure if June is been able to unmute herself at this time. June, are you available to chat about the upcoming geochem work?
Actually, if we have a minute, can you let's go back to the maybe the second slide.
Can you hear me now?
Okay, no, okay, so we can go back to June.
Okay, am I live now? I'm sorry.
Yes, you're live.
Okay, this is just quickly a few exploratory geochemical modeling tasks that I'll be working on this year. You know, there is always, it's very difficult to extrapolate from solid rock data and mineral data and arsenic in the minerals to what a potential arsenic concentration might be in during ASR cycle testing. But we have so much data at Kissimmee River ASR that I'm going to try to do something with that. We're using, you know, standard geochemical modeling tools. The FGS has a huge database of rock data and mineral data, and also it'll be supplemented by new mineralogical reports and maybe even the FGS, the Florida Gulf Coast University study. So that's the first task. Next slide, please. Another thing, it's always this magical thing called a buffer zone. You know, the buffer zone is a mixed zone of some composition that is based on conservative mixing using chloride and also, well, traditionally using chloride. One of our goals is to limit the amount of sulfate in recovered water. So I want to compare, mixing volumes and buffer zone composition between using chloride and then compared to sulfate, both in the chloride in the Upper Florida Aquifer and the APPZ. Next slide, please. And this is going to be a fairly straightforward effort, is just to look at the geographic occurrence of radium in the existing DB Hydro data set, in both the Upper Florida Aquifer and the APPZ. This is really just to look at the geographical distribution to see where this might be an issue. Again, the best strategy with radium is to leave it in the aquifer. And so we want to find out where there might be elevated concentrations of radium, primarily in Lee and Collier counties, I think. Okay, I think that's probably my last slide. Thank you.
Thanks, June.
All right, and I just want to go over what our expectations are for the peer review panel and the ASR science plan next steps. So what we're envisioning is that each panelist is going to prepare a memorandum based on the presentations that they heard and saw today. And also they were provided the draft 2022 ASR science plan. So that should be considered when they prepare their memo, and that memo will be submitted to the chair, Dr. Messmer, by June 30th. The chair will be responsible for compiling the memos into one consolidated 2022 peer review panel report. And the district is anticipating this report to be submitted to us by July 15th. This peer review panel report will become an appendix in the 2022 ASR science plan. The district and the Corps will revise the draft science plan based on this report. And this process will take about a month or so to complete. So we're estimating that work to be done by August 30th. After that date, we will plan on reconvening with the peer review panel in early September sometime, and plan to release the 2022 ASR science plan for public review in mid-September for a 30-day time period. Just like last year, comments on the ASR science plan will be accepted via email or in letter, and they will be incorporated into a comment response matrix. And you may recall that the comment response matrix was posted on our website for everyone to view. And we're hoping that this will all be completed by November before the end of the calendar year. Just please keep in mind that these dates are tentative and sometimes do shift, but this is what we're planning on as of right now. So just as a friendly reminder, tomorrow's event is only open to the peer review panelists and the project team members. We will plan on meeting tomorrow morning at 9 a.m. and open it up to the panelists to ask questions about the ASR science plan or any of the presentations that they saw today. We do not intend to have any formal presentations and no new material will be shared, but we will have the presentation from today available in case there's anything in particular they'd like to discuss or go over. And just for all of our other attendees, we will be posting today's presentation and the recording of our meeting on our website within the next few days. And for further information, please visit our website at the links shown below at the bottom of the slide. So once again, I'd like to open it up one last time for any final comments or questions from our peer review panelists. And just like before, if you could use the raise hand feature and to submit your comment. Any closing remarks? Okay, I see one hand raised. Dr. Renee Price, please state your comment.
I want to thank all the speakers and everybody and their team that worked on the presentation today. I want to say good job, and I look forward to seeing you all in person tomorrow.
Thank you. All right.
Yeah, hey gang, this is Bob Arastro. So the plan for tomorrow is for the panelists to meet in person, for those who care to travel and meet with us in person, to meet at the district headquarters at 9 o'clock tomorrow. And we'll have a brief conversation or discussion with whatever remaining thoughts or comments you might have from what you heard today. And then I have got a van that should be able to transport whoever wants to ride with us up to the Kissimmee ASR site. And then we're going to have, we'll meet in the city of Okeechobee and grab a quick bite to eat before we mobilize out to the Kissimmee ASR site. So I would suggest that you wear cool, comfortable clothing and a hat and something like that. So that we can walk around in the sun. Hopefully we'll have a good weather during the early part of the afternoon. And we'll try to get you all back here at the district for those who wish to travel with us by 5 o'clock at the end of the day tomorrow.
All right, thanks Bob for covering those logistics. Any other comments from the peer review panel before we close out for the day? Okay, I do not see any hands raised, so I just want to thank everybody for their time today, and we appreciate your interest in the ASR Well program and the annual update of the ASR Science Plan. Enjoy the rest of your day. Thank you.